Hello everyone, very good evening to all of you. How are you all? I hope every one of you is doing absolutely fantastic. This is your chemistry expert Sanjay Arya sir, and today we have another important session on D and F block. So hopefully I'm live and I'm pretty much audible to every one of you. Am I audible, everyone? Yeah, so previously we finished one of the chapter from this block chemistry. We call them block chemistry, a very important part of the inorganic chemistry. Recently we finished P block, and now is the time that we should finish D and F block, one of the very important chapter. Yeah, hello Shivam. Right. So our target is to complete 3D, 4D, 5D and 6D series, their atomic, physical, chemical and their periodic properties, their important compounds, and then we will study F block, which are 4F and 5F. We call them Lanthanides and Actinides respectively. So now beginning the chapter from very first thing, that is the introduction to all of these D series. What is the meaning of D series? There we have the very first series that start from the fourth period. Remember everyone, this series starts from the fourth period. We call it 3D series. We call it 3D series. Starts on scandium, ends to scandium, titanium, vanadium, chromium, manganese, ferrum, cobalt, nickel, copper, zinc. Try to remember all the elements just like I have learned them like that. Similarly, coming to the another 4D series, we have yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium. This comes in fifth period of the modern periodic table. Yes. Later on we have 5D series. 5D series is lanthanum, hafnium, thorium, tungsten, delta, then we comes to gold and mercury. This is your sixth period of modern periodic table. And that is why I sometimes say that modern periodic table, if someone remembers the entire modern periodic table, the part of individual block chemistry becomes highly easy for them, because they know where is the location of every single element, what kind of property do they show. Everything is very much rememberable if you know the modern periodic table very well. Then we have 5D series, and later after that, from actinium they start at actinium, and then rutherfordium, diborgium, sigorbium, bohrium, like that, hessium, mendelevium, and then till CN we have seventh period, the last period of modern periodic table. And let me take you to the group. So this starts from group number 3, group 4, group 5, group 6, 7, 8, 9, 10, 11 and some scandium, titanium, group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, correct. 9, 10, 11 and 12. So till 12th group, group number 3 to group number 12, we have entire block called as D block. And in D block, so how do we define the blocks and all? We all remember, like in P block, what did we study? That in the writing the electronic configuration of an element, the last electron, the valence electron, goes to P subshell, and it was used to called as P block element. Similarly here, the last electron will be reaching to D block, and that's why we call them D block elements simply, right? So they are also called as transition metal except group 2L. So guys, all D block elements from group 3 to group 11, they are called as transition metals, but the elements of group 12, which are zinc, cadmium, mercury, They are called as pseudo transition metals. We call them pseudo transition metals. Now, meaning of pseudo transition metal means, since these elements from 3 to 11, they have at least one unpaired electron probably in their ground state or in their excited state or in their normal oxidation state or in their higher oxidation states, they always have number of unpaired electron, and that unpaired electron undergoes transition. That is why we call them transition elements. Now, coming to the 12th group. 12th group has zinc, cadmium, mercury. They have completely filled d subshell, no unpaired electron left for the transition. That's why they are called as pseudo transition elements, and they are not considered as the transition element, just like the other elements of D block. Notes of periodic table is not uploaded. It's okay. Thank you for your feedback. I will let everyone know, and they will upload the notes of periodic table as soon as possible. Even I'll make it done by the end of the day. Thank you. Then we have, coming to their IUPAC. According to IUPAC, the transition metal are defined as the metal which have incomplete d subshell in their neutral or their ionic state, and their general configuration is NS122 N-1 D 1 to 10. So guys, always remember this. It's the general electronic configuration. Although somewhere you will find that their electronic configuration is not as smooth as we were earlier using that thing in writing the electronic configuration for p block element, because d block elements have different type of some sort of exception in them because of the poor shielding of d orbitals. D subshells have poor shielding, and that causes more Z effective, and thus electronic configuration differs somewhere. So you will find so much anomalies while writing the electronic configuration. Not panic, don't worry, I will reveal whatever the configuration exception is there. There we go. So here what do we see? That out of all the given element, only these elements are the one which will be having anomalous or exceptional electronic configuration, which is copper, chromium. We all know about 3D series, guys, right? We know this is your 3D series, 4D series, 5D series and 6D series. So in 3D series, chromium and copper are two elements that have exceptional configuration of, rather than writing 3D 4s2, we write them 3D 4s1. Okay. I think I must give you all the idea of electronic configuration from scandium, titanium, vanadium, chromium, manganese, ferrum, cobalt, nickel, copper and zinc. I think I must give you the idea how do we write the electronic configuration. Writing down their atomic number, this is 21, 22, 23, 24, 25, 26, 27, 28, 29 and 30. At least for 3D series, we must take an idea what anomalous behavior or what exceptional electronic configuration I'm talking about. So guys, scandium comes with 21. The recently ended period is third, and the element was, last element is a noble gas, argon, which ends with the third period. Then you have come to fourth period, that starts from 4s2, and then 4s, then comes 3d. So 18 is here, 18 plus 2 is 20, 20, and then one electron is needed, 3d1. So this is the beauty of d block element, that you will find the electronic configuration such a way that whatever the atomic number is here, like 20 plus 2, that plus 2 amount will come up into your D subshell. Take this example, argon, 4s2, this is 20, then this will become 3d2, this is 22, this is 3d2, and 20 plus 2, like that. Vanadium, we have argon, 4s2, 3d3. Similarly, this was supposed to happen in this way, but it is 4s1 and 3d5. Rather than going for 4s2, 3d4, this goes with 4s1, 3d5. One electron jumps from s to d. And why is it happening? The main reason behind is the poor shielding. And this configuration is relatively more stable because of the This is more stable because of the half-filled D subshell, which is comparatively more stable electronic configuration. So this is some exceptional behavior we are seeing. So let me just highlight the part. Next is manganese. The configuration will be same, 4s2 3d5. Iron has argon 4s2 3d6. Then we have 4s2 3d7 for cobalt. Then same applies with nickel, argon 4s2 and 3d8. Now again you will come to one exception, argon 4s1 3d10. So this is also one of the exceptional part we can see. Why is it so? Because the fully filled electronic configuration is relatively more stable than that of 9 electron. 9 electrons are more stable, lesser stable than 10 electrons. This is another. And finally, we have zinc that we were earlier talking about. It doesn't have any unpaired electron. That's why we cannot consider zinc as a transition metal. It is simply argon 4s2 3d10, completely fully filled electrons. That is why this is not an not a transition metal. So guys, these two what we are writing are supposed to having the exceptional electronic configuration. Hai? So always take your notes, take your notebook with you, start making the notes properly. That will help you to sit for longer hours, longer duration you can sit, and you can learn whatever I'm teaching you, right? Instead of unnecessarily sitting and just spending your time. The most fruitful thing is over here. Or you can do one more thing, you can start making your short note, so that will be highly helpful for you for revising the complete notes. And you must also have, you can collect our complete notes from the Telegram channel. The link is given in the description. Thankfully, moving forward. So these are the electronic configurations which are found to have a bit exceptional electronic configuration, exceptional from the regular electronic configuration that we write for these elements. And please remember this part, always learn this part, because previously in some of the JEE Main attempts I have seen such kind of questions appeared in the exam. So I think this is an important part to remember. The anomalous part has been asked so many times. Always think of this, that even I have come up with their proper electronic configuration. So this will be highly helpful for you writing down their electronic configuration. Now, I hope this part is absolutely clear to all of us. I have explained these two. Then we have niobium. Niobium, where is niobium? Over here. It was supposed to have an electronic configuration of 4d5 and 5s2. Sorry, 4d5 4d4 and 5s2. Sorry, 4d3 5s2. Just like take this example. For example, if we talk about niobium, niobium belongs to 5th period and it is 4d series. The latest, the recent finished 4th period element, last period element was your krypton. So its electronic configuration is krypton 5s2 and 5 minus 1 4d. This must come with 3, but no, it doesn't exist like this. In actual, it exists like this. Niobium has an electronic configuration of krypton 5s1 4d4. So very different and very strange. This is how it happens. So what I'm trying to say you that you got to learn these all, and that's why I have come up with this very detailed notes where you can take this as an idea that where can we find such exceptions. So whatever it comes under this line, they all will be having the similar kind of exception. They all will be having 3d10, 4d10, 5d10 like that, and one electron will be there in the another subshell of NS subshell. Take this example: copper 3d10 4s1, silver you can see 4d10 5s1, gold we have 5d10 6s1, and then Rg. So I have clearly mentioned here whatever the exceptional behavior is there with the electronic configuration, you got to know about it from here. Then we have classification of D block. Classification as in the d orbital transition element extend more towards the outermost surface of an atom, and then S and P, and that is what I said, they are bigger in size, and yes, they are more influenced by the surrounding as well as affect the atoms or molecules by the surrounding atom. So ions in the given DN configuration have certain characteristics and properties such as display of the variety of oxidation state formation and formation of colored complexes, colored ion, and entering into complexes formation with the variety of ligand catalytic property. This is something that you do not find very usual for the S and P block element. That's why D block elements are special. We can use them as catalysts because of their variable oxidation state. We can use them as their as complexes or the central metal atom or ion. That will continue in our upcoming session called as coordination compound. There you will come to know how D block elements are used there as central atom. Some ligands come with their lone pair and they put their electron pair there, forming coordination bond and forming a complex. So that what we study in next class. So this is the beauty of D block element, which is not possessed by the S and P block elements. There are greater similarities. Once, because as we all know, they have poor shielding with moving from left to right. They have poor shielding of D subshell. More and more electron you are adding, more and more reduction in size will take place, and that is something that keeps their properties similar to each other. There is no greater differences in their property. There is a greater similarities in the properties of transition element of horizontal row in contrast to the non-transition elements. However, some groups similar also exist. So there are some groups which are also exist with the similarities. Same kind of properties can be seen in the groups. Take this example, group 11, we call them coinage metal because they all have that properties of high temperature being molded into coins, great malleability, flexibility. These elements are copper, silver, gold, like that. Let us have some questions here. Let us have some questions, everyone. Now we have some questions to answer. Try by your own. Oh yeah. So among the following series of transition element, the one where we have D2 configuration, 3D2 configuration, what do you find the correct answer? Tell me. Where can you find the correct answer? Tell me. So let me try 3D2 is something what's needed. 3D2. So scandium, titanium. Let's say titanium 3+ I'm taking. So guys, argon has 18 electron and titanium has atomic number, scandium, titanium 22. So what will happen? After 3+, this will form argon, 4s2 and 3d2. So 4s0 and it will become 3d1. That means it is incorrect. Now picking the next one, titanium plus and vanadium 4+, scandium, titanium, vanadium. So let's say vanadium 4+ I'm taking as an example. We know scandium, titanium, vanadium. Vanadium has an atomic number of 23. So 23, argon, 4s0 because of this 4 plus, and 3d also has become scandium, titanium, vanadium, 4s2 and 3d1 will be seen. So this is also incorrect, I guess. B is also not correct. Now let's try C. Titanium 4 plus, scandium, titanium. Titanium 4 plus will be your incorrect answer, will not have 3d2, I guess so, because titanium 4 plus, its atomic number is scandium titanium 22. It has argon 4s2 3d2. So 4s0 and it will become 3d0. Again, this is incorrect. So this is also incorrect. Now, I guess only one option is left with us now. Titanium 2 plus, vanadium 3 plus. Let me check one of them. Let's say titanium, we are talking about 2 plus. So this is argon 18, scandium, titanium 22, 4s0, 3d2. So whenever you remove an electron, the first electron will be removed from the highest principal quantum number, that is 4s. So vanadium 3 plus, even we talk about scandium, titanium, vanadium. 23 is the atomic number. Argon, this has become 4s0 and then 3d2. 3d3 it was supposed to be, but 2 and then 1 electron is been removed from the 3d3 and like that. So I guess this is the correct answer. D is the correct answer. नहीं हुआ ऐसी होने यार. तूने 2 बोला था कि 3 बोला था? अच्छा 3 नहीं चला किसी में भी यार. Now moving to the next question. Try this by your own, everyone. Try this by your own. Scandium is a transition element, but zinc is not. Why? Because it has what? Fully filled D subshell. And that is why we do not have no unpaired electron. We do not have any unpaired electron. That's why it cannot undergo transition. It's not a transition element. It's even a pseudo transition element. So the correct answer should be the last electrons go to no, both scandium no, both zoop in the scandium 3D. Yes, D is correct. B is correct. B is the correct answer. Hi, hello to everyone, guys. Actually, I'm not ignoring anyone, but I'm just expecting this chapter should be covered or by done in coming 4 hours, 3 hours, whatever it takes. So that's why I am just continuing with the concept and with this chapter to go on. So whenever any doubt comes, anything you need to ask me, just post it in the comment section. I'm continuously watching it, might not be responding on your hi and hello, but don't worry, I'm not ignoring anyone, okay? Let us move to the next question. Which of the following ion you find has an electronic configuration argon 3d6? What do you think? Argon 3d6. D6 is something that means, okay, so I can write it by everyone. This is argon, then 4s0. Why 4s0? Because outermost electron, 2 electron will be removed. 1 more will be removed, 3d8, it will become 3d7. This is argon 4s0 and it will become 3d4. This is atomic number of 26. So argon 3d6 is it was there and 4s2. So first 4s0, 2 electrons are removed, 1 electron will be removed from here, it will become 3d5. Cobalt has an atomic number of 27. Argon 4s2 3d7 is its atomic number, but making it 3 plus, this will be 0, and from 7 you are removing 1 to 3d6. So I think this is correct answer. D should be the correct answer. Try it by your own. There we have another question. Which of the following are D block elements but not regarded as transition? We all know group number 12. Group number 12, zinc, cadmium and mercury. What we call them? We call them pseudo transition elements or metals. Pseudo transition metals we call them. Now we have come to their physical properties. Right after their electronic configuration and some general discussion about them, we have reached to their physical property. We'll read their physical properties once and then we'll come to their periodic properties such as their atomic and ionic radii, their ionization enthalpies, their metallic nature, their so many things are there basically need to discuss. But first let us discuss about their physical properties. Since we all know all of them are typical metals, in fact every element belonging to D block and F block are metals. Everything is metal. They are high, they have high tensile strength. That's why iron with its alloys with carbon forming steel. Steel is used as making these steel rods. Ductility, it is used for making wire just as copper. Malleability, we all know that gold is most malleable and it is used in making some ornaments, gold ornaments. Then their high thermal conductivity, due to which they are used in making utensils. They have higher conductivity, they are used to make the wires such as copper, silver, we have aluminium wires. Metallic luster, they shine while we, they have shiny appearance, right? Gold, how fascinating is gold, huh? Isn't it? Gold is very fascinating. Gold gives a very unique kind of shine and that's why gold is very fascinating, huh? Very expensive also. Now we'll come to their structure. Whatever I'm teaching you, it's a very depth thing, very in detail thing I'm providing you. No requirement of rote learning anything, especially coming to the physical property related to their packing in which they exist, because this belongs to a part called a solid state where it has been not studied these days. It has been eliminated. The solid state chapter has been completely eliminated from JEE main point of view. But anyways, we just can take the idea. You will find that some of the element may exist into different crystal lattices also. But yeah, take this idea that with an exception of zinc, cadmium, mercury and manganese, they all have more than one. So zinc, cadmium and mercury are supposed to have only one kind of or one type of, only one type of crystal lattice they form or they exist in. Take this example, zinc and cadmium and all, they have hexagonal closed packing. We call such packing as AB type packing. AB type packing, we call them AB type packing. And that all happens because of the, like this is one layer, you can see this is one layer A, this is another layer B, this is one layer A. So AB, repetition is something that keeps on happening. Then guys, we have cubic closed packing structure, which is also one of the very common structure found in copper, silver, gold, platinum, nickel, very common, okay? And the correct examples, like we all know that zinc, cadmium, mercury, all others have different type of structures also. And what do we define it with? This is called as ABC type packing. ABC type. Again, I'm telling you, no need to rote learn anything, but just take an idea what metal belong to what kind of structure, how does this structure is made, and what is the repetition of the layers, just like AB, A, or ABC, like that. The last one is your body-centered cubic lattice. Body-centered cubic lattice. So body-centered cubic lattice structure, There are some elements which exist in BCC packing, and the examples are scandium, titanium, zirconium, hafnium, like that. Now we'll move forward. Okay. The second property, like initially we studied with the physical properties, and physical properties such as sonority and ductility, malleability, all the properties that usually some metal show. Now we have some properties related to the melting and boiling point. So this is very important one. This is some very important part that we are going to cover. First thing, okay, boiling points are very high for all of them because these all typically exist into metal. So metal first will be having their molten state at some higher temperature. Right after that, you need to vaporize it into gas. That temperature will be typically high. The boiling point is very high for every one of them. Now, if we talk about the melting point, so melting point, always remember that melting point is something which is directly proportional to the number of unpaired electron. Higher is the number of unpaired electron, so higher is the extent of metallic bonding. Melting point is directly proportional to this, it is directly proportional to the extent of metallic bonding. Remember this part. Melting point will be directly proportional to this. We all know that coming to manganese has the highest number of unpaired electrons, 5 electrons. Manganese. In the D subshell we have. No. Manganese we do not have highest. Chromium has the highest one. Chromium has 3D5 4s1. See, chromium with the highest. Chromium, molybdenum and tungsten, they all come under the same group. And then the very next one has the kind of like lowest one, manganese, technetium, rhenium, and it decreases abruptly, right? And it keeps on decreasing while we move to the end of this series of 3D, 4D and 5D. Just like you can see, copper has the lowest one, then gold and then silver, light here. Anyways, copper has higher melting point than even gold and even with silver. But exceptionally, gold was supposed to have higher oxidation, higher melting point than gold was supposed to have lower melting point according to this graph, but gold is in between copper and silver. Now we have enthalpy of atomization. Now again, the similar portion or similar kind of graph you can see. This graph and this graph, there is no as such differences, right? Again, this is your chromium and this was tungsten and this is molybdenum, I guess. Like this. This is your rhenium, technetium, TCMN, Re, manganese. We can see the same pattern over here also. That if we again talk about the enthalpy of atomization, so enthalpy of atomization is directly to the number of unpaired electrons. So higher is the number of unpaired electron, higher is the or stronger is the metallic bonding, and there will be higher amount of energy required to dissociate two metal atoms into metal gaseous atoms in order to break down the metallic bond. This is what their order is followed. Third one is density. So guys, talking about the density usually increases moving left to the right, and it reaches to the maximum. It reaches to the maximum somewhere up to copper. And what do we see? So guys, this is absolutely database thing. That is why I'm asking you to make your own short notes, which will be highly helpful for you to remembering the points, and you can easily recollect the information whenever it is needed. So this is supposed to be having the maximum density. This is what having the maximum density in 3D series, right? Not in up to all the period, just in the 3D series. Copper has the highest one, and then for zinc it slightly decreases. So usually what we can say that moving left to the right in the 3D series, it keeps on increasing. So the highest density, who has the highest density? Just remember there are two elements with the topmost densities. Number one is osmium, 22.51 gram per cc, and iridium 22.61 gram per cc. Iridium has higher even than osmium. Yeah. I'm looking at the comments also, guys. I'm looking at the comment, and don't worry. Thank you for your precious feedback you showed me. Thank you for your appreciations and your moving next to the atomic radius. Now we are in the world of anomalies. We are in the world of D block elements, which do not have anything very normal. They have very different and very odd kind of behavior, whatever the property we are dealing with. Now next property is your atomic and ionic radius. And atomic radius has been seen, which is the metallic radius over here. It's been seen that moving left to right, first it decreases, then it reaches to somewhere where it is almost constant, then again it increases. That is how the pattern works. Let me tell you that if you only talk about the 3D series, if we only talk about the 3D series from scandium, titanium, vanadium, chromium, manganese, ferrum, cobalt, nickel, copper, zinc, the variation is like this. Till here it decreases. Till here to here it remains constant, and then from copper to zinc it increases. So radius increases, radius remains constant, and radius. So what we explain this pattern all about? We simply say that why is radius decreasing? Because from here to here, what do we see? Z effective increases, because increases the Z effective, decreases the radius. Then here to here, Z effective is almost same, is almost constant, and then from nickel to copper and zinc, Z effective decreases. That is why the radius increases. Remember this explanation. Similar kind of pattern has been observed for 4D and 5D also, as we can see. So what do we observe? That d orbital contraction is something, and it's very common, guys. What is the meaning of contraction? Contraction means decrease in the size. Why does contraction occur? Because d orbitals or d subshells have high Z effective. Why it is so? Because of their poor shielding. Poor shielding. What is the meaning of poor shielding? So guys, the meaning of poor shielding is that whenever we add electrons do not repel each other very much, because it's a large size, it's a huge sized orbital which can accommodate electrons with no too much repulsion, and that causes like with extra electron there comes extra proton. Like whenever we keep on increasing the atomic number coming from one element to another, like scandium, titanium, vanadium, chromium, we are continuously adding one extra electron and one extra proton. So what does it give to us? It increases the proton, which are increasing the effective nuclear charge, but electrons are not repelling. That means poor shielding is occurring and high Z effective, which leads to decrease in the size called as d orbital contraction. As I told you that from scandium to chromium the radius keeps on decreasing. Then I told you from there to copper it approximately remains constant, and then suddenly it increases. So no such questions has been asked earlier about their exact data, that what will be the radius. No, and you don't need to even remember it. Just take this thing in your account, take this thing as an idea, the pattern where it decreases, then constant, then increases, like that. That is what very important to us. Okay, thank you everyone. Thank you. Hunter, I'm reading your comments. Don't worry. And thank you for motivating me to have my own classes and all. But I think whatever it's working, it's going good, and let us focus here on the chapter only. That was very curious of you. Thank you. We have another important term to study. So guys, I will lead you with one more important part from here called as lanthanide contraction. So what do we see that you might have observed this part, that we have scandium with us, then we have titanium, scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper and zinc here, 3D series. Then we have 4D series, as in yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, or up to cadmium. Right. Then we have lanthanum. Now I'm teaching you what is the meaning of lanthanide contraction and why is it very important to all of us. A good number of questions usually come from this particular concept, and there are so many properties which are actually affected using this lanthanide contraction only. So, just like inert pair effect we studied previously in P block, inert pair effect was very common there in every group. What was that about? That is all up to because of the lanthanide contraction. So lanthanum, hafnium, therium, tungsten, rhenium, like that, and it goes up to mercury, Hg. Then we have actinium, rutherfordium, diborgium, seaborgium, and up to Cn, I guess, Cn. Coperincium, something like that, I don't remember the name. So what I'm telling you, what I'm trying to tell you is that if you go with their atomic number, this is 21, and believe me, their magic numbers also work in this pattern. What I'm trying to show you, that their magic number works in 18, 32, and then from here also 32, 18, 32. But in this pattern, what do we see? 18. Then this lanthanum, right after lanthanum we have 32 and we have 32. Now you might be wondering, what are these numbers? We call them magic numbers. Magic numbers are directly connected with their atomic number. You can find out the atomic number. 21 plus 18 will be 39. 39 plus 18 will be 47, not 47, 57. 57. And 57 plus 32 will become 89. So this is what their atomic number is. But their atomic number is a bit different. Here we have 22, very simply. Here we have 40. We were supposed to have it 58, but this is not 58. This is 72. Now this is somewhere the magic has begun. This is not 90, this is 72 plus 32, 104. So what do we see, sir? There is something missing in between the lanthanum and hafnium. How many numbers are missing? 14 elements are missing. Yes, everyone, we are talking about these four. These 14 are called as lanthanides. These rest 14 after actinium are called as actinides. Take this thing in the account. That atomic number has changed in coming to the 3D series. Or see, there was nothing in the 3D series we found. 3D series were highly normal. We found 4D series here. But when we reached to the 5D series, reaching to the 5D series, we found that there is a huge gap between two element, consecutive element, lanthanum and hafnium. And there is a gap of 14 elements that are actually lanthanides, and we call them 4F series. And similarly, actinides are called as 5F series. So that is what their distribution is all about. And what we are studying is the lanthanide contraction. We still haven't come to this conclusion, what is this lanthanide contraction. So guys, what happened, just like d orbitals have poor shielding, f orbitals also have poor shielding, and they keep on continuously decreasing their size while moving left to the right. So let's say if I'm talking about, this is the atomic number and this is your radius of the ion in, let's say, picometer, and from here to here we are starting. Let's say we are going like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and let's say 15. So what I'm bringing here, let's say this is La3 plus, lanthanide, lanthanum La3 plus. Then we have the next element Ce3 plus, Pr3 plus, Nd3 plus, Pm3 plus, take this idea, Laurentium at the LW. Now guys, what you see, what you observe is what I have written over here is it's simply the differences. It's a graph that we can see that radius of this metal 3 positive ion, because metal 3 positive is the most common oxidation state shown by the lanthanides. So this is the lanthanum, and right after that start the lanthanides. So this is cerium, then promethium, and like that, NdPm, SM, EU, and then we have GD, this is gadolinium, TB, DYHO, and coming to this LW is your laurentium. Okay, no, not laurentium, lutetium, this is Lu, this must be Lu. Anyways, I'll write it Lu3 plus, lutetium. So this is what we call as the lanthanide contraction. Lanthanide contraction. What is the meaning of lanthanide contraction? That due to, why is it happening? Due to poor shielding, due to poor shielding of F sub shell, the size of, okay, poor shielding of the Z effective of lanthanide strictly increases and their ionic radii. What is the meaning of ionic? M3 plus radii strictly decreases, the radius strictly decreases, called as lanthanide contraction, called as lanthanide contraction, LC. So this is what the meaning of lanthanide contraction is. Lanthanide contraction is actually nothing but the decrease in the size of lanthanides, very strict decrease in the size, and called as lanthanide contraction. So what effect can you see because of lanthanide contraction? Over here you will find, see, so effect of LC, effect of lanthanide contraction. Due to effect of lanthanide contraction, what you will see, the radius of yttrium and lanthanum and even actinium, they are very there's a gap actually. So what do you see, that yttrium is smaller than lanthanum, but zirconium is greater than that of hafnium. Check it out. This is the effect of lanthanide contraction. Okay, lanthanide contraction is leading to decrease in the size, even you are having an extra shell there, because while coming from zirconium 40, zirconium coming to coming from zirconium 40 to hafnium 72, we have increase in the size. We should have increase in the size because of addition of another shell, but because of the extremely poor shielding and high contraction in the size decreases coming from zirconium to hafnium, and that is what I was earlier talking about. So this has so many effects. Not just this, let me tell you one more thing. One more example is here. Ionization energy 1 of, when we move down the group, ionization energy decreases. So copper has ionization energy higher than that of gold, sorry, that of silver, but ionization energy of silver is even lesser or smaller than the ionization energy of gold because of its poor shielding, or poor shielding as in because of the lanthanide contraction. This is what happening due to lanthanide contraction. So now there are ionization enthalpy. We talk about ionization enthalpy, and we can see that ionization enthalpy is kind of like very simpler pattern. Moving left to the right, ionization enthalpy is actually increasing. Okay, again I can see it's roughly arranged 631, 656, 650. So it's not a proper pattern there which has been observed here, no regular pattern basically. So there are some of the anomalies we can explain, everyone. We are not supposed to rote learn every single element and its ionization enthalpy. What we can do is we can simply go for the explanation for some of the anomalies, such as one of the exceptions. Second ionization energy of manganese is lesser than that of chromium, and first one is greater than that of chromium. Manganese is lesser, but manganese has first higher than that of chromium, because manganese has electronic configuration 4s2 3d5, which is a stable configuration, and 4s1 3d5 was that of chromium. So easily one electron can be removed. But after removal of one electron from 4s1, chromium becomes 3d5 and it becomes 4s1 3d5. So where can it go? So this has become more stable now. So the removal of electron is very difficult from Cr plus rather than Mn plus. Mn can easily lose 4s1 electron, but it cannot lose easily 3d5 electron, more stable. One of the perfect example I gave you. The another example is here, that second ionization of zinc is less than that of copper. Why is it so? And first one is greater for zinc, because zinc has a fully filled electronic configuration of 3d10 4s2. Removal of electron is very difficult because it was already having a stable configuration. Coming to copper, it had 4s1 and 3d10. So 4s1 can be easily removed. But once after removing the 4s1 electron, now copper has become more stable, which has acquired a 3d10 configuration, and 4s1 electron has been released. So now, because of its more stability, it has higher ionization enthalpy than that of zinc plus. In the similar way, we have another such example of third ionization enthalpy of manganese is more than that of iron. So you can check out their electronic configuration. You can conclude exactly the same thing that I have done for these two examples. You can do it for third one. I'll move forward and we'll reach to the final conclusion, the graphical analysis, where you can see all the elements with their respective ionization enthalpies. This graph is not to be memorized. I again told you, there is no need to rote learn this graph. Just take an idea how how does it vary. So taking this scandium is here, scandium, titanium. Where is titanium? Scandium, titanium, vanadium, chromium, manganese, ferrum, cobalt, nickel, copper, zinc. It's a rough kind of graph. Let's try some of the questions from here, everyone. Let us just get the clarity what kind of questions comes in an air examination, what kind of question come and how do we respond them. Take this example. Here is one question. The question says that the transition element that has lowest enthalpy of atomization. So lowest enthalpy of atomization for least number of, we need to have the least number of unpaired electron, as I told you, and zinc could be the perfect answer. There is no unpaired electron. There is no unpaired electron. But no, it's not about just, man. This is something to learn about, guys. This is something to learn about. Where was the enthalpy of atomization? Here. Okay, we see. What do we see, by the way? Copper. We don't see any such example here, na? Oh my God. Anyways, that's a factual data. Maybe I misinterpreted it. Metals to the second. Okay, anyways, let me just check their value. It's a theoretical question. Let me just check their value. Let me just get their values. Enthalpy of atomization of copper, and it has 338 kilojoule per mole. Okay, now let me check the same thing for 338 was for copper, zinc, and zinc has 128, the lowest enthalpy of atomization. So guys, we are absolutely correct, and there is nothing to be troubled about. We already had the perfect idea we thought of. So copper is incorrect. Let me just cut this thing, and only correct answer is D. So I was just checking because it's a factual data. We must not attempt any question incorrectly. I was just checking it, okay, whether in the question has it been given different, but no, it was not. The data also corrected itself. Correct answer should be D. Try this question. The pair that has the similar atomic radii. What do you think? Which pair must have the similar atomic radii? What do you think? How should we think of this? similar radii. Actually, it was there that 4D and 5D have nearly same radii. How so? Let me show you. How is it? Let me show you. Check it out. Now these two are actually mixing to each other. You can see these two are doing what? Mixing to each other. So this is your, this green one is your 3D, blue one is 4D, and this one is 5D. So atomic radii of 4D is no doubt larger than 3D, but 4D and 5D, they have nearly similar, and this is because of the lanthanide contraction, because from 4D to 5D it comes with the lanthanides. Now reaching to our same question. But there is no, okay. Think of it. So this is your 4D element, this is your 5D element. So this is the correct answer. Rest all you can see manganese 3D, 3D and 5D, 3D and 4D, 3D and 3D. So the correct answer should be 3D and 5D have the nearly same size. Why do they have the same nearly? Due to lanthanide contraction. It all happens because of the lanthanide contraction. The third ionization enthalpy will be minimum for, like, which of these has the minimum third ionization enthalpy? What do you think? Third ionization enthalpy should be minimum. How should I know it? Third ionization enthalpy minimum. After losing 2 electron or after losing 3 electron, it must acquire a stable configuration. Definitely after losing metal, after losing 3 electrons in its M3 positive state, it should acquire most stable configuration. Most stable configuration. Now check it out. Most stable configuration, where do you find? Cobalt 3 plus. Check it out, everyone. Check it out. So this is argon 4s0 and then 3d6 it will become. Not so stable. Ferrum 3 plus. Argon 4s0 3d5. Yes, most stable. Then we have nickel 3 plus. We have argon 4s0 and 3d7, not so stable. And then manganese, this has become argon 4s0 and 3d4. The only correct answer is, I guess, B. Somewhere we can apply our mind. There is no need of rote learning everything down. Wherever it is required with rote learning, I will let you know. But till now, we haven't found anywhere where we are supposed to rote learn the part. It is all about apply the concept, get your answer. Next question. The lanthanide contraction is responsible for the fact that zirconium, zinc have same oxidation state, and no logic behind that. Zirconium, hafnium, zirconium, where was zirconium? Deuterium, zirconium, niobium, lanthanide, hafnium, and they have same. Yes, zirconium, hafnium have more same radius, correct. And yes, as I told you, because where does it come? See, scandium, titanium, vanadium. We have yttrium, zirconium, niobium. We have lanthanum, hafnium, therium. So what it is asking is, we know that there comes the lanthanides. They are the lanthanide contraction. So the lanthanide contraction leads to us that radius of yttrium is lesser than the radius of lanthanum, but radius of the zirconium is approximately equal to the radius of hafnium because of lanthanide contraction. Because of the poor shielding, even we are increasing one shell, even we are increasing one outer shell, the radius has not increased into that much significant amount because of the lanthanide contraction. B is the correct answer. The correct order of first ionization enthalpies. Now you got to tell me the correct order of first ionization enthalpy is what? Actually, this is not easy to tell. First ionization enthalpy. I guess zinc must have the highest one because zinc had the most stable configuration of 3d10. So basically most stable, and the most stable will be having most ionization enthalpy 1. Logically we have reached to this answer. Next question. The correct order of the decreasing second ionization energy of titanium, vanadium, chromium, manganese will be what? So second ionization energy should be what? Correct. So okay, do one thing, either you make their first positive or just try to make second positive ion, so that we can conclude which can of them have the highest one. So just take their metal positive. So their metal positives will be, let's say if are having scandium, titanium, vanadium. Okay, let's start with titanium plus scandium, titanium. So it will be having electronic configuration of argon 4s2 and 3d, sorry 4s1, 3d2. Then we have vanadium plus argon 4s1, 3d3. Then we have scandium, titanium, vanadium, chromium and manganese. Chromium will have argon 4s0 and 3d5, and manganese has argon 4s1, 3d5. Question is pretty similar, pretty simple. We got to assign them in increasing order of their atomic. Their ionization energy we got to find out, and that too second one. So this is, what do you think, which can of them release easily? And this is how. Chromium is actually having the most stable, I can see. This is somewhere you can see the most stable, will be having highest ionization enthalpy. Check it out, highest for chromium. C option is the correct one. C option is the perfect. C is the correct answer. Next property is their oxidation state. Now, after finishing their periodic properties, some of the general periodic properties and the physical properties, now we have come to the chemical properties, and the very first chemical property is none other than oxidation state. So, the transition element may show greater variety of the oxidation state in their compound, and what do we see that the maximum number of multiple oxidation states are being shown by here manganese. Check it out, guys. This is one which is showing us the maximum number of oxidation states. Maximum number of oxidation states are being shown by manganese. Apart from that, I think it's visible, perfectly visible, right? Yeah, it is kind of. So scandium has a positive 3 oxidation state. These are something which are having just single oxidation state, like scandium. In zinc, copper also shows +1 and +2. The red one are their most common oxidation state where you can find these elements in their combined state. So note that the common oxidation states are in the red, with these are having fixed oxidation state. Scandium 3+, Zn 2+, cadmium 2+, like that. And then the element which have the greatest number of the oxidation state occur in or near to the middle of the series, where you can find the maximum number of unpaired electron that will be having highest number of this oxidation state, and the maximum number of oxidation state of the reasonable stability corresponding to the value in the sum of the S and D. Okay. It's not about the unpaired electron, it is all about the maximum number of electrons which are available in S and D. Maximum oxidation state of reasonable stability compound is in the value of the sum of the S and D up to manganese, is followed by a rather abrupt decrease in stability of higher oxidation state. So it increases the higher oxidation state up to manganese only, but right after manganese we have iron, cobalt, nickel, copper. We have continuously decrease in the oxidation states. Talking about their special feature of oxidation state which we just studied. For D block element, their oxidation states differ from each other by unity. With addition of one more electron, their oxidation state also vary with the 1 unit, right? 1 unity means 1 point. Yes, definitely, Ashwin. You already know the answer. Ashwath. Definitely, this will help you not in just JEE Main, but also for the advanced point of view. This content is an exclusive content. You can find the best content in India. You can find it. The only thing that you got to do it by your own is to revise it properly, make some short note out of it, try solving some of the question with it, and then solve PYQs. You will be very much flexible and comfortable solving the PYQs. Where were we, by the way? We came that from D block element. And in the oxidation state, we are talking about their special feature that their oxidation state different by the unity, because with the addition of one electron, their starting for this scandium, titanium, vanadium, their oxidation state usually increases by 1 parameter, and then later on it decreases by 1 parameter, 1 magnitude. Group 4 to 10, if we talk about the higher oxidation state, are favored by the heavier members, which is opposite to the P block element, because in usually when we used to see that moving down the group, if we talk about moving down the group in P block, inert pair effect used to work, that used to reduce down the oxidation state. So let's take this example of carbon. Carbon is very much comfortable in positive 4 oxidation state, but talking to lead or tin, they do not show +4, they show usually +2 oxidation state because of the inert pair effect, where NS2 electron become inert. Talking about their D block element, they do not have such problems in that, and that is why they show even more number of oxidation state. The example is that molybdenum has +6 oxidation state. Molybdenum has +6. tungsten has positive 6, are more stable than chromium with positive 6, and thus chromium in 6 forms Cr2O7, strongest oxidizing agent, when MO3 and WO3 are not the oxidizing agent. They are very stable even at that positive 6 oxidation state. Now we should move forward to the low oxidation state we're talking about. So guys, lower oxidation states are found when a complex has ligands capable of pi acceptor characteristic in addition to the sigma bonding. For example, nickel tetracarbonyl, iron tetracarbonyl. So what is it saying? Let me tell you. Why is it showing low oxidation state? Whenever there is some kind of ligand or there is some kind of compound which is attached to these particular metal atoms, but these metal atom which they are connected with the ligand is not having any particular charge on them. Usually we see that chloride, cyanide or isocyanide or any kind of hydroxide, oxide, they all have a negative charge over them, and that makes a positive charge oxidation state on the central atom to make an overall molecule a neutral molecule. What we are having is just carbonyl, carbon monoxide doesn't have any charge over that, and that makes a central metal atom with zero oxidation state where whatever it is attached with. So in metal carbonyl usually we have metals with zero oxidation state. So that low oxidation state is also stable. And why is it stable? Because of the presence of these ligand which are carbonyls. I guess that's enough for this oxidation state. Let us try solving some questions and then we'll move forward. The very first question from oxidation state is, which one of the following exhibit the large number of oxidation state? Manganese is the king of all of them. It shows you various varieties, and the highest oxidation state is also positive 7, and chromium doesn't show up to that even. The element that usually does not show you a variable oxidation state was one scandium with 3+ and zinc with 2+. Always remember these two: scandium 3+, zinc 2+. Next is trends of stability of higher oxidation state. If we talk about trends in higher oxidation state, we talk about. So I don't know what it is, but we can study it, we can read it out. So chromium can show halides in case of halide, and in case of oxide we will talk about. Two things we'll talk about. One of them is oxide, the another one is halide. Starting with halide, talking about the halide, the winner is chromium with CrF6. Learn it guys, because this is something which is absolutely rot learning thing. Just learn it. Vanadium also exists in the pentoxide, and these are also some relatively more stable states. Manganese usually is stable in its +4 oxidation state like this, and also some of the dioxides also exist. CuX, CuX2, ZnX2 like that. So what is the meaning of simple X there? The meaning of simple X is fluorine to iodide. Everyone can make these compound. And what is the meaning of X dash? X dash, wherever you find X dash, that iron can make compound up to bromine only. It doesn't make compound with iodine. Iodine with the bigger size is not stable with iron. What is X double? Double means even reducing one more halogen from there. Fluorine and chlorine only we are using, not using bromine and iodine. And X triple dash means only chlorine, bromine and iodine, removing fluorine. Fluorine doesn't make any compound with them. So try understanding. These are exclusively very in-depth notes you are available with. So guys, do revise it on time, and believe me, you can crack your exam, whatever the exam you are preparing for. The highest oxidation state are achieved is TiX4. The highest oxidation state, oxidation number are achieved by TX4, tetrahalite, VF5 and CrF6. Manganese positive 7 is not found in the simple halide, but MnO3F is also found, which is also having a positive 7 oxidation state. Beyond manganese, the only trihalide known is the FeX3, and where X could be fluorine, chlorine and bromine, but cannot be iodide. Cobalt trifluoride also exists. So now talking about fluorine can establish the can stabilize the highest oxidation state because of its higher lattice energy in the same case of CuF3, or higher bond energy in the case of higher covalent bond tendency VFI, CRFI. For V plus phi, the halides other than VFI undergo hydrolysis to give oxo halides, such as oxo halides means oxygen and halogen compound, VOX3. So another feature of fluoride is their instability of low oxidation state, example VX2 and CUX, like that. The another feature of fluoride is their instability. So this doesn't happen. VF2 doesn't exist, CuF2 doesn't exist, only exists is CuCl2, CuBr2, CuI2, VBX2, VBr2, VI, like that. Okay, CUX, not CUF. This is only CUF. CUF doesn't exist. CUF2 does. All these Cu double means oxidation state in +2. Halides are known except iodine, because iodine, why doesn't it make? Because iodide, with iodide it oxidizes. Iodide ion with -1 charge goes to 0, it is been oxidized. Copper 1 +2 comes to +1, where it is reduced. Very important reactions are there, everyone. Try making their short notes and try to learn them. Then in many of the copper 1 complexes or compounds in aqueous solution, it undergoes disproportionation, where it can easily undergo oxidation reduction by itself only. This is in +1, this is +2, and this is 0 oxidation state. Then the stability of copper 2 positive aqueous, then copper 1 plus, is because of their much more negative enthalpy of hydration. You must agree with this part that Cu positive has an electronic configuration of argon 3d 4s0 3d 9 3d 10, sorry, and Cu2 plus is argon 4s0 3d9. So it seems like copper plus is more stable than copper 2 plus, but it happens in gaseous state. But in aqueous state, copper plus is lesser stable than copper 2 plus, because in aqueous state, this more negatively charged, this more positively charged copper ion 2 plus, cupric ion, we call Cu2 plus as cupric, and we call Cu plus as cuprous. Cupric ion is more stable because of the higher hydration energy. Always remember this point, that in gaseous state this might be more stable because of the electronic configuration is fully filled, but in aqueous state Cu2 plus is more stable. Then we have trend in the stability of higher oxidation state. Trends in stability of higher oxidation state in oxides. Earlier we discussed about the halide. The winner was chromium hexafluoride. Let's see here who wins. So manganese, manganese has the positive 7 highest oxidation state. Then chromium has +6 oxidation state. Vanadium has V2O5 pentoxide, where positive oxidation state exists. And apart from that, everything exists in a mixed form. So apart from these oxides, mixed oxides also exist, where you can see manganese Mn3O4, like MnO dot Mn2O3. This is your Mn3O4. So the oxidation state is +2. This is +3. And the average is 6 plus positive 8/3. This is what we call as the mixed oxidation state. Trends in the stability of higher oxidation state we are talking about earlier. For the oxides we are right now discussing about. The ability of O to stabilize high oxidation state. The ability of oxygen to stabilize high oxidation state exceeds of that of fluorine due to the ability of oxygen to form the multiple pi bonds with the metal also. So that is why there are more number of oxygen can be attached. The highest oxidation state is shown in group 7, coincides with the group number. What does it mean? Highest oxidation state in the oxides of group 7. Group 7 is your manganese group, manganese wala group, that group 7. And no higher oxides of iron above Fe2O3 are known. However, it can form ferrates up to positive 6 oxidation state in alkaline medium with FeO4 2 minus ion. But they are readily decomposed to give you Fe2O3 and oxygen. Besides of the oxides of oxocation are also stabilized. Oxocations are cations with positive charge with oxygen. So vanadium VO2 plus has an oxidation state of positive 3. Sorry, positive 5. Then this is VO2 plus is positive 4. Positive 4. Order of increasing oxidation state VO2 plus to Cr2O7 2 minus to this is due to the stability of the lower oxidation state to which they are reduced. Okay, this is the oxidizing power. This is what we are discussing is the ability of oxidizing power. Oxidizing power means they work as oxidizing agent. And why they do so? Because the so formed cation or so formed oxidation state they go under, like MnO4 from positive 7 state goes to positive 2 state, and which is more stable. That is what it's saying, that lower oxidation state in which they are reduced will be more stable. So that's why that makes permanganate ion more oxidizing power, more like better oxidizing agent than the VO2 positive or Cr2O7 2 minus positive. Cr2O7 2 minus permanganate. We have this F2O7, we'll study about it, and its structure you can see. This is how its structure look like. There is one peroxy bond and rest all are the oxy bonds. This is your peroxide bond, and rest all are the oxide bond. Okay, there was no question directly the answer. Okay, let's see what is the answer. The question says that which of the following transitional metal atom can form stable oxide oxocation? I know vanadium was known for it. I think vanadium. I think we studied that VO2 positive is the one which is stable in positive 5 oxidation state. Which of the following ion does not liberate hydrogen gas on reaction with dilute acid? What do you think? On reaction with dilute acid, which of them does not give? Well, I have no clue. But yeah, that concept can be added because the most stable one won't do it, I guess. Most stable one. So try writing the electronic configuration and find it out. Let's say if you are starting from titanium 2 plus, scandium titanium, argon 4s0, and then it will become scandium titanium 3d2, argon 4s0, 3d1, argon 4s0 and 3d5. This is the correct answer, I guess. तो So manganese doesn't liberate because manganese is already very stable in state, and in order to liberate, manganese need to go into Mn zero oxidation state, है ना? Mn what is happening here? H positive liberate hydrogen gas. So acid will be having its H positive ion going into H2 under reduction. So Mn2 plus must go for higher oxidation state by losing more electron, but Mn2 plus is already stable, and as I told you, why is manganese force manganese plus 7 Mn2O7 or MnO4 minus are very highly strong oxidizing agent? Because their lower oxidation states are very stable. Lower oxidation states are stable. So Mn is stable in Mn2 plus, doesn't want to go under higher oxidation states. Then another chemical reactivity we have, everyone. Another chemical reactivity includes E naught values. Okay, allow me a sec. I'm checking the order only. Actually, there was a point I'm missing, and I thought, where is it? Maybe we'll study it probably in the preparation of, like in the study of other elements. Fine. So now we have another important chemical property that is called as the I think now it's good. It was unnecessarily having highlight here. Chemical reactivity with E naught values will be studying. So guys, this is something that we have to directly learn, and I don't think there is a point of rote learning the values, but just take an idea how we are giving them different values. So this is how it varies, and in electrochemical series we already have gone through the values. We all know that copper comes below hydrogen. So copper is the one that has the most highest SRP value, and rest of the other metals have lesser SRP values. They are more reactive metals than copper. They can and even below hydrogen copper exists. So copper cannot replace H plus ions by copper plus ions or Cu2 plus ion to liberate hydrogen gas. Rest others can do it. So like talking about Mn2 plus 2m, if we are talking about Mn2 plus 2m, just this is the idea, just take this idea. The minimum value of potential, this is your SRP value, and I guess this is highest for copper only. You can check it out, everyone, check it out, this one. And the same if we go for metal 3 plus 2 plus, then this part is a maximum for cobalt. 3 plus to 2 plus is maximum for cobalt. Because of the very high Z effective of cobalt 3 plus, it accepts easily one electron, forming Mn2 plus. Now we'll directly reach to some question. We'll try solving some question, and then we'll reach to the other milestone to achieve. The M2 plus 2M standard electrode potential is lesser for, which one has the lesser one? M2 plus 2M. This was it, M2 plus M, I guess copper. Okay, no. Copper has positive this too, and manganese has 1.18. So the electrode potential is lesser for. Why is it lesser, man? I think manganese has it lesser. Don't we think? See, copper has E naught Cu2 plus 2 Cu, positive का 0.32 34 volt. And if we are talking about manganese, so this has highly negative value 1.18. So I think the correct answer should be A. The reduction potential is lesser for A. Next is, which one of them is a stronger reducing agent, Cr2 plus or Fe2 plus, Cr2 plus or Fe2 plus? Which one of them is a stronger reducing agent and why? So as a reducing agent, what you need to do? As a reducing agent, you need to oxidize yourself. Cr. Stronger reducing agent. They need to, if a reducing agent is there, that will oxidize itself, so it will go to Fe3 plus electron, and this will, let's say, go for Cu3 plus electron. Now you check it out, which of them is having higher value for this. Here you can find it out. See, using this data you can find it out, this data. Same for 3 plus 2, 2 plus, you have to check. So their reduction is happening and we got to identify the what is happening over here is reduction. That part is reduction. And here we have to oxidize them. So it is like reverse of the one. So which one is having higher value of M3 plus to M2 positive? Iron has a positive value. Chromium has a negative value. So going from 2 plus to 3 positive, I think chromium will be the correct answer. Why? Right? Because E naught of Cu 2 plus to Cu, not Cu, Cr. No, yeah, 3 plus to 2 plus we are going, no, 2 plus to 3 plus. So how much is this given? 2 plus to 3 plus we are checking. 3 plus to 2 plus is given to us. Chromium has positive 0.41 and minus 0.77. So which is the correct one? Chromium. So that's how we define it. Guys, we already have studied electrochemistry. We already have covered so many good part of redox reactions. So this is something which we can relate even by our own. No need of rote learning everything. The data was already given to us. We can use that data. I don't know why was I going for that data. Data is given over here only. Check this out. Check this out. This is important data. 4 successive members of first transition series, which is 3D series, right? Which we are talking about transition metal. It is your 3D series. And these are listed below. So for which of them the standard potential EM3 will be the highest? We all know for M3 positive to 2 plus. I think this is for cobalt. And this data is a factual. I told you to learn it directly. D. Why plus 2 is more stable? Because of higher hydration energy. What is the relationship between chemical reactivity and E0 values of D block element? Like they can become good reducing agent, oxidizing agent dependent upon their values of E0 cell. Next is 4 successive member. Oh, we have completed it already. No. EM2 positive to M now it has been asked. The value with the highest positive sign is the only one. I told you copper is the one that has the maximum value, and even it lies below hydrogen in the electrochemical series. That is why it makes its SRP value even more than the other members. Other all members have negative SRP value. This has a positive SRP value, positive 0.34. Which one of the following transition reactive can form stable oxide? Oxocation and anion with oxygen in higher. I think vanadium is fine. VO3 plus and VO6 and other vanadium oxides are also formed. This question was appeared back in 2017. The question says that which of the following ion does not liberate hydrogen gas on reaction with dilute acid? So it could be copper or it could be manganese, because it is the most stable. Most stable cation and doesn't get reduced. Magnetic properties, we'll talk about magnetic properties. So guys, magnetic properties are very common for all the transition element and their compounds, because they have unpaired electrons. So what you need to find out is the number of unpaired electron. Number of unpaired electrons. If you know the number of unpaired electrons, then you can say that it will be paramagnetic, and if it is not having any number of unpaired electrons, it will become diamagnetic. You can find out the value of magnetic moment, which is called as spin only magnetic moment, root n into n plus 2. The unit is Bohr magneton, BM, right? Then magnetic properties, we have scandium. This is what you can find it out by your own also. And let me just give you one more idea here. The another idea is like whenever you are being given with the value of mu, and let's say your mu comes up like this, A point BCD type. If your mu is A point BCD, then remember this part, this A will represent the number of unpaired electrons. You may take any example. Take this example. Let's say if n is equals to 1, then mu will become what? N into n plus 2. So it will become 1 into 1 plus 2. This is under root of 3. So 1.732. Can you check it? This one. Take another example. Let's say n is equals to 2 is here. Mu will be how much? Root of 2 into 2 plus 2. So it will be like under root of 8 Bohr magneton. Value of Bohr 8 will be somewhat like 2.92, let's say. Now again what you can find is this 2. Remember this technique of identification of the number of unpaired electrons very fast, very easily using this concept. See this thing. So guys, keep on liking the session, everyone. Keep on liking the session. Those who haven't liked the session, do like the session. So now we will come to the formation of colored ions. How do they form the colored ions? They form their colored ions because of DD transition, mostly due to DD transition. What is the meaning of DD transition? We all know that d orbitals are the degenerated d orbitals are 5 d orbitals belonging to a particular subshell, dxy, dyz, dxz, dx square, y square and dz square. Now all of them have different shapes and sizes, and due to which, okay, what will happen, this is how it is represented. This is your dx square, y square. So these two are axial. These two are the axial orbitals, and these three are non-axial orbitals. So what happened whenever when an electron moves from lower energy or to the excited, actually this is what happens when they form complexes and d orbitals. Whenever these transition elements form octahedral complexes with 6 ligands interacting with the central metal atom or ion, the ligands face directly towards the axis, plus x minus x, plus y minus y, plus z minus z. All the orbitals which are oriented toward the directions of incoming ligand, they get excited, they get more energy. So dxy, dx square, y square, dz square, these two orbitals get more energy, and they there is a splitting of the energy occurs, and degeneracy is lost for the d orbitals. The lower energies will be acquired for the dxy, dyz and dxz. The energy difference between these two is called as the crystal field splitting energy, and this is the only thing responsible that any electron from the lower energy state, that unpaired electron, can jump to the higher one and can show the color. So wherever you will find there are number of unpaired electrons, those unpaired electrons can go under transition called as dd transition, and dd transition leads in the formation of some color. That's it. So you can check out some of the colors here. You can check out. There is no need of rote learning it, but just take an idea, guys. Take an idea. Okay, potassium permanganate is also colored, and K2Cr2 also is also colored, but they are not colored because of the mechanism of dd transition. Instead, they are colored because of the. Why are they colored? Because of charge transfer, we say. So this is something that we'll study later on in our upcoming chapter, when I'll teach you about the complex compound or coordination compound. Then I'll tell you two kind of mechanisms responsible for the colors in complexes. One of them is called as dd transition or FF transition. Another one is called as charge transfer, metal to ligand charge transfer, ligand to metal charge transfer, ligand to ligand charge transfer. This is what it keeps on happening. Just take an idea, no need to rote learn what color what an ion shows, but just take an idea, okay. The ions having no unpaired electron will be usually colorless or whitish in color, and the color in aqueous solution are given below. Some of the colors are given below, which we do not need to rote learn, just take an idea and move forward. We have formation of colored ions here. Just check it out, everyone. For all the colored ions, just find out where can you find the number of unpaired electron. With the number of unpaired electrons, you can see which of them can be colored, which of them cannot be. Next property, after colors, we have next property called as catalytic property. And we all know that d orbital, like d block elements, can show variable oxidation state. This variable oxidation state is actually helpful, having them the catalytic property. Take this idea that whenever this reaction was carried out, it used to take a lot of time. But whenever the same reaction is carried out in the presence of iron 3 positive as you were here, and which automatically converted itself into Fe2 plus, and then at final this 2 plus got into Fe3 plus, the reaction carries out fastly. So because the transition metal ion can exchange their oxidation state, they become more effective catalysts, and for example iron 3 plus can catalyze the reaction given below. More number of examples are vanadium Phi in contact process. What is this contact process, by the way? Contact process, formation of sulfuric acid, है ना? In P block we study. In Haber's process, N2 plus 3H2. And in nickel in catalytic hydrogenation, alkenes or alkynes undergo hydrogenation with the addition of hydrogen giving alkanes in the presence of nickel, platinum, palladium, like that. Next is formation of interstitial compound. What is the meaning of interstitial compound? Interstitial compounds are the compounds which are formed by entrapping small sized atoms of hydrogen, oxygen, nitrogen, carbon in the interstitial spaces of the lattices which are formed by these transition element. Just take this idea, just like titanium chloride, magnesium nitride, iron hydride, these all represent the what we say them interstitial compound, and they could be stoichiometric and they could be non-stoichiometric also. Non-stoichiometric as in because there is no as such fixed ratio in which hydrogen is bonding. There is no bonding there happening. Just hydrogen atoms are coming. They found there is a gap between the lattices and the interstitial sites. They got their own places. Such type of compounds are called as non-stoichiometric compound, and they are interstitial compounds. The formula shown of these compound does not correspond to any normal oxidation state of these metal. Yes, absolutely. And the principal physical and chemical characteristic of these compounds are, since these elements have some external element coming in them, which are hydrogen, carbon and nitrogen, I told you, they have high melting and boiling point than the pure one. They are very hard, and some of the borides approach to the diamond in the hardness. They retain their metallic conductivity. Their metallic conductivity is retained there, and they are chemically inert. They become chemically inert because there are already some of the entrapped metal atom or ions which are reacting with the existing metal and doesn't let the metal react with the external or another elements. So they become chemically inert. Their chemical reactivity does not increase. Their metallic conductance remains same, and even it increases, and they become very hard. They also have higher melting and boiling point. Oh my god, how many properties are there? So many. Anyways, we'll take a break short while. Right after finishing all the chemical properties, we'll take a break. Then we'll connect back and we'll start with the rest of the remaining topics. Now we have alloy formation. So alloys, you all know, it's a homogeneous mixture of metals. There is no chemical bond takes place between the metal atoms in alloy. There is it's a metallic solution we have. Alloys are formed by atoms which with the radius must be about 15% to each other. Okay, so delta R should be lesser than equals to 15%. Two metals that can go under alloy formation must have similar radius or must have similar radii, and if not similar, they should have a difference of around 15%, not beyond that. The alloys are generally hard, have often higher melting point. Best non-alloys are iron, carbon, chromium, vanadium, tungsten, molybdenum and manganese. These are used in the preparation of steel. Brass has copper and zinc, bronze has copper tin. That is what you are studying from the class 10 standard, right? Even in your childhood, you might have heard of these two, brass and bronze, very important alloys. How many are left here? Okay, the last one. Then oxides and oxo ions of metal we'll talk about now. Oxides are generally formed by the reaction of metal with the oxygen at high temperature. All the metals can form the oxides, and they are typically ionic in nature, except scandium. They are which are okay. So scandium form metal oxide, which is Sc2O3, I guess, scandium oxide, and which are ionic in nature, and rest other have both of the characters of ionic and covalent. As the oxidation number of metal increases, the ionic character also decreases. Okay, that is what we have studied in the Fazan rule when we were studying the chemical bonding. Higher is the oxidation state of the metal, higher will be the generated polarization. Higher is the polarization, higher is the covalent character. In the higher oxides, the acidic character is predominant. Okay, in higher one, like Mn2O7 will be more acidic than the other one, gives you HMN4. manganic acid, permanganic acid, and it gives you H2CrO4, which is chromic acid kind of like. And V2O5 is amphoteric in nature, though it mainly oxides, and it gives you VO4 3 minus as ion as well as VO2 plus salt. Vanadium, there is a gradual change from the basic V2O3 to less basic V2O5, V2O4, and gives BO2 plus salt, which is acidic with acid, sorry. And what is this written? Let me just read it. Vanadium, there is a gradual change from the basic to less basic behavior. Okay, from V2O3 to V2O5, if you go from higher oxidation state, as you can see here, the oxidation state is positive 4, here the oxidation state was positive 3. There is a gradual change, you can see, and V2O5 becomes N2 amphoteric V2O5. This is amphoteric, basic, less basic, and this is amphoteric. This is positive 5. CRO is basic, and Cr2O3 is amphoteric. Let's try some solving the questions. Which of the following shows a magnetic moment of 2.84? As I told you, if it is 2.84, the number of unpaired electron will definitely be 2. For 2 number of unpaired electron, let us check out the electronic configuration. Nickel has an atomic number of 28. Cobalt, that has a 27. So cobalt will become what? Argon, 4s0 and 3d7. This is argon, 4s0, 3d8. So let us arrange 8 electrons in 5 orbitals. 1, 2, 3, 4, 5, 6, 7, 8. The number of unpaired electrons are coming as 2. And if we go with cobalt, filling these electrons 1, 2, 3, 4, 5, 6, 7. There are number of electron 3. Correct answer A. There was a question came in JEE Main 2014. The chloro compound with vanadium has a spin-only magnetic moment of 1. So guys, you all know that number of unpaired electrons must be what? 1. Now check it out. Vanadium has 2 plus. Vanadium with 3 plus. Scandium, titanium, vanadium. So vanadium, scandium, titanium, vanadium. Vanadium 3 is 4s0, 3d2, 2 electrons. Then this is 0 electrons. Vanadium 2 plus could be the correct answer, I guess. So this will become argon, 4s0 and 3d3. No. N is equals to 3. It is also incorrect. B is correct, I guess, because in B, what we can get is, if we talk about the B option, so vanadium is actually 4 plus here. 4 plus vanadium will give you what? How many unpaired electrons are there? Argon, 4s0 and 3d, 2 electrons are removed, rest 2 will be removed, 1. N is equals to 1. This is correct. B option is correct. So guys, that is how we use this concept, and such questions have been asked in JEE Main. Kind of similar question can be asked in your upcoming exams also. So just have a grip over this command and over this concept. Most of the transition elements form alloys and show catalytic. Yes, true. True, because of their variable oxidation state, they show catalytic property, and because of their similar sizes, not so much different in the sizes, they can undergo formation of alloys also. Which of the following arrangement does not represent the correct order of the property stated against it? Paramagnetic behavior is proportional to the number of unpaired electron. So check it out, guys. How many unpaired electron can you find? I guess in iron, 2 plus 6 electrons were there. Number of unpaired electrons are 4. Manganese has number of unpaired electron 5. I guess this is the correct one. This is actually incorrect, and that is what it was asked. Let's see others if we can find it out. So the number of oxidation state, manganese, this is so true. I guess this is also true. I guess A is correct. Which of the following ion species will impart color to an aqua solution? Which of the following ionic species will impart color to an aqua solution? So the one with having any unpaired electron. So 0 unpaired electron, it has 0 unpaired electron. Scandium, titanium, it has 0 unpaired electron. It has also 0 unpaired electron. It has non-zero electron. 3 plus 2 will be removed from that. 3d4. 3d3. So it has 3 electrons. This is the correct answer, D. This is how you can do. Brass is in, I told you brass, copper plus zinc. Which of the following statement is interstitial is incorrect? They are much harder, true, true. They have higher melting point, true. They retain their conductivity, true. They are chemically reactive, no. They are chemically inert. They do not react very frequently. Then another question is, calculated spin only magnetic moment for Cr3 plus ion is Cr2 plus has 3d 4s0 and it has 3d3. So number of unpaired electrons are actually 3. No yaar, it's 4. 3d4. Aqua solution containing which of the following will be colorless? So colorless will be for that which will be having 0 unpaired electron. A is correct, I guess. Which of the following characteristics of the transition metals is associated with their catalytic action? High enthalpy, no. Paramagnetic, no. Color, no. Yes. Variable oxidation state is responsible for their catalytic property, as we saw in one of the given example there. Next is some important compounds. So we'll continue and we'll resume our class after a short break. We'll take a short break of 15 minutes. We'll resume our class by 18:20. So guys, we'll continue from here, and we have a small portion of this chapter left with us. That is, number one is some of the important compounds, and number two is F block. So let us first continue with the two important compounds of D block that is in our syllabus and very important to us. And I think as far as the concern of JEE Main, these have been removed, but anyways we'll continue them and we'll finish them. Like these are highly important in as far as the concern of advanced. These two compounds are potassium permanganate KMnO4 and K2Cr2O7 potassium dichromate. We'll go a bit fastly from here. Hopefully you all have come back. Are we guys all here, guys? Hope so. Now we will come to one of the important compound called as potassium permanganate KMnO4. What is KMnO4? What are the properties of KMnO4? Let us discuss it all. First of all, how is it prepared? It is prepared from pyrolusite, which is an ore of manganese, MnO2, manganese dioxide. MnO2 is basically heated in the presence of potassium hydroxide in basic medium, and on oxidation it gets converted into potassium manganate, which is K2MnO4. Right after that, while subjected it to some acidic medium, it disproportionates itself and gives you manganese dioxide MnO2 plus KMnO4, which is your potassium permanganate. Now this KMnO4, whatever we are getting, MnO4 minus, is actually a very good oxidizing agent also, because it is having the highest oxidation, highest possible oxidation state of manganese. It can only undergo reduction. So something itself undergo reduction will be a strong oxidizing agent. Commercially, it is prepared by alkaline oxidative fusion of pyrolusite followed by the electrolytic oxidation of manganate. Okay, the same thing is happening here. First you are making manganate and then you are undergoing in acidic medium disproportionation reaction producing permanganate and MnO2 again. This is how its appearance look like, some sort of purplish colored crystal you can find. And laboratory, how can you synthesize it? In laboratory, we can have this manganese 2 positive ion, a salt which is oxidized by peroxide disulfate, permanganate ion to permanganate actually. So Mn2 positive is here, right in the presence of S2O8, which is nothing but peroxide disulfate, and where it is in positive 6 oxidation state. Itself it goes for sulfate ion, it is converting back into manganese, is converted into Mn plus 7 here. Manganese is converted into plus 7. Maybe it is a half reaction, I guess, because I don't see the reduction part here. Okay, where is it? Okay, wait, allow me a moment. So kindly read it out, everyone. Please read it out. Then we have properties, and what comes under the properties? Its physical properties, such as it forms dark purple, its appearance is dark purple, almost black kind of crystal, and crystals are isostructural with KClO4, which is a tetrahedral molecule, KClO4, potassium perchlorate. Right. So exactly like this is how the structure looks like, a tetrahedral species, and in the similar way potassium permanganate also looks like. Like this, potassium permanganate. It's not very much soluble in water, and when it's heated it decomposes at 513, giving back potassium manganate, dioxide and oxygen. So remember these are very important reactions which we are right now dealing with, and these reactions will be highly important for us. Even in the examinations, these questions have been asked previously. You will find some of the PYQs related to the same. Then we have properties. What are its properties? It's actually two important physical properties are its intense color and its diamagnetism. Diamagnetism because manganese actually over there is in +7 and there is no unpaired electron we can find. Since there is no unpaired electron, we can declare them as diamagnetic in nature. The manganate and permanganate ions are both of them are tetrahedral. They form p-pi d-pi back bond, p-pi d-pi bonding, pi bonding they do. So this is manganate which is green in color. Manganate ion looks like this. K2MnO4. So there are two O minus charge like this. Mn is present in +6. Mn is +6 in nature. +6 has one unpaired electron, due to which it becomes paramagnetic in nature. Coming to permanganate ion, Mn has one negative charge ion over here, and this manganese with +7 oxidation state has 0 unpaired electrons. That makes it diamagnetic in nature. So manganate is paramagnetic and this is we already know. Now next properties. Potassium permanganate is an important oxidizing agent. Different possible half reactions for the reductions are as follow. So let me just give you this idea. Manganese MnO4 minus is actually present in +7 oxidation state, and it may undergo some set of reactions depending upon the medium, such as in acidic medium, it gets converted into in neutral medium and in highly alkaline or basic medium. Now check it out everyone. Basic medium we have OH minus ions. So MnO4 is undergoing acidic. In acidic medium it reaches to Mn2 plus. In basic medium it reaches to Mn4 plus and Mn plus 6 it reaches. MnO4 2 minus MnO2 and it is MnO or MnSO4 like that. So it is in +2 oxidation state. Okay, no need to write. The ion itself is confirming the oxidation state. N factor we can write. N factor will be how much? +7 to 2 it is 5. N factor over will be +7 to 4 it is 3, and N factor over will be 7 to 6 is 1. This is how we use the N factors for their what is it happening by the way? Yeah. We already have covered this part in redox reactions, but it's important and we should take these things into account. So many things are very much interrelated. H positive concentrations of the this plays an important role, as we all have seen here, and kinetics of the reaction is also very important factor here. Permanganate at H plus is equals to 1 should oxidize water, but the reaction is extremely slow unless either manganese 2 plus ions are present in the temperature. It is. That's a good point actually. Try reading out this point, that what is the kinetics has to say about the reaction. Permanganate ion, MnO4 minus ion, at 1 molar H positive ion should oxidize water, but reaction is extremely slow unless either manganese 2 ion are present or temperature is raised. So guys, Mn2 plus over here, Mn2 plus ion over here works as a catalyst, and that is why it basically reacts faster or makes the reaction occurring faster, and higher temperature also favors this reaction, might be an endothermic process. Now let us just come back to the main important chemical reactions. What kind of reaction does it show? Now some of the reactions you will find where you can see all of these redox reactions have been mentioned here. So we all must know that what is the reactant and what should it go into what oxidation state, and then we can manage it by our own only. Let me just give you one example, everyone. Let me just give you one example here. Take the first equation. How many iodides? I minus simply take, and one is MnO4. Now you will see how easily, and let's say we have been given with the acidic medium. So in acidic medium we all know where this MnO4 minus go, this goes in Mn2 plus iodine will be oxidized to I2. Now check it out, everyone, check it out. Oxidation state is -1, here it is +7, here it is +2, here it is 0. If something is going from -1 to 0, the n factor will become 1. If something is going from 1 to this, the n factor will become what? 5, right? So now do one thing, just cross multiply with the n factors and get whatever the possibility we can get. So it will be like what, 5 times of I minus, 5 times of I minus plus MnO4 minus, and it produces Mn2 plus I2. So just balance it, make it 5 by 2, or it is the same only, and then you can multiply the whole equation by 2. So you will get what? 10 times of I minus plus MnO4 minus 2 times gives you 2 times of manganese 2 positive ion and 5 times of iodine. So right after getting this, if it is acidic medium, you can balance this equation. How do we use to balance in the redox reaction? Now once the electrons have been balanced by cross multiplication of n factor, now you need to balance the oxygen. How many oxygen atoms can you see in the left hand side? It is 8. In right hand side it is 0. So put 8 H2O and just 16 H plus over here. This is your balanced chemical equation. So we don't need to rote learn any kind of reaction over there. We can easily determine the reaction. We must know what is the reactant, what it will go into, in what medium. If we know about all of these things, then we can directly apply and we can find out whatever we need it. So guys, take this idea that it converts iron 2 positive into iron 3 plus. The highest possible oxidation state of iron is 3 plus. Oxalate ion C2O4 has an oxidation state of carbon as positive 3, which can be oxidized further into CO2, that is plus 4 oxidation state. We have hydrogen sulfide H2S as -2, which can be oxidized up to 0. No, H2S is where? It can be oxidized to 0. Then sulfurous acid has an oxidation state of positive 4, can be converted down into positive 6 in the sulfate ion. And similarly, nitrite ion can be converted into nitrate ion. Positive 3 oxidation state can be converted into positive 5 oxidation state, because we all know about this potassium permanganate, which is a good oxidizing agent. Then we have next one, in neutral or faintly alkaline medium. There is already something, the idea we already have about where does it lead to go. Itself gets converted into positive 4 oxidation state, as I told you earlier, rather than positive 2. Positive 2 actually happens into acidic conditions. This is positive 7. Iodine is undergoing -1 to positive 5. This is one of the very important reaction. It has been asked, and that's why I'm star marking it. Guys, why am I star marking this reaction? Because it is highly important. It has been asked once in our JEE Main examination, PYQs. So you will find the same question right after this. Like while we'll be going for solving some question. Iodine in its positive 5 oxidation state goes when it is like iodide was reacting with permanganate ion in basic medium, faintly basic medium, neutral medium kinda. Then thiosulfate S2O3 will go for sulfate ion for the maximum oxidation state of positive 6, right from its oxidation state of 2x minus 6 equals to -2 plus 4 oxidation state, I guess. No, it's not. Positive 2 only. Then manganous salt is oxidized. Manganous salt means Mn2 positive is oxidized to MnO4, and both of them are getting back into positive 4. This type of reaction is called as symproportionation or comproportionation reaction. How? Because the reactions in which two different species from different oxidation state reaches to the same oxidation state. You can check it out. This one is present in positive 2 oxidation state. This one is positive 7 oxidation state. Both of them are reaching to the same oxidation state. Such type of reactions, I have already termed them. They are called as comproportionation or symproportionation reaction. But majority of the reactions we carry out in the presence of sulfuric acid only. We do not carry out these experiments in HCl, because Cl minus can be oxidized up to Cl2, ClO2 or Cl anything, but it can be oxidized, right? And giving you unsatisfactory results. That's why the reactions are carried out in the presence of sulfuric acid only. This is what it is written there. Let us talk about their uses. Potassium permanganate. Where do we use potassium permanganate? Potassium permanganate is used in analytical chemistry. Analytical chemistry as in like in titrations. अरे यार क्या प्रॉब्लम है इसकी? Yeah. So we use it in analytical chemistry as a as an oxidizing agent. Used as a favorite oxidant in the preservatives of preparations of organic chemistry, and very simple reaction you can see. For an example, there was an OH group attached over here, and let's say this is H, so it will get converted into like this. Okay, ketone it can be converted into. Then bleaching of wool, cotton, silk and other textile, and then decolorization of oils. This is what its uses are. Shape we all know, tetrahedral. Manganate ion, even it is manganate or permanganate, the only difference of the O minus part, 2 O minus are there in manganate, 1 O minus is there in permanganate. Incorrect statement about manganate and permanganate. Manganate is actually paramagnetic because it has one unpaired electron, because its oxidation state is positive 6, and permanganate has positive 7 oxidation state, all the electrons are gone. This is diamagnetic. Manganate is purple. No, this is incorrect. Manganate ion is actually green and permanganate ion is purple black in color. There is a question, everyone. Try solving this question. Actually, this question is based upon the preparations of KMnO4 only. So I think that's an easy question. Thermal decomposition of manganese compound X on 513 Kelvin results in a compound Y, MnO2 and a gaseous product. Okay, so I know this gaseous product is no idea. Thermal decomposition of Mn compound. Okay. Compound Y. Gaseous product might be oxygen, and MnO2 reacts with NaCl. Pungent gas is released, XYZ or what. Anyways, I think this reaction is we are thermally decomposing there was a reaction, I remember. KMnO4 potassium permanganate upon heating produces K2MnO4 plus MnO2 plus oxygen, I guess. And so decomposition of a manganese compound, I guess this is your manganese compound, and it produces what is this compound? Compound Y, and this is your gaseous product. Then MnO2 reacts with NaCl, MnO2 reacts with NaCl and concentrated H2SO4 concentrated H2SO4. I don't know what is this reaction about, but I guess this will definitely give you a pungent gas Z. This could be, how can it give you SO2? I think it will give you Cl2 only. So probably this reaction will go for A is the correct answer, na? Kx was KMnO4, Y is K2MnO4, correct, and Z will be Cl2. And no reaction is given here. Anyways, I'll check it. Guys. I'll check it. You keep on searching the correct answer and let me check it for a while. Let me check it, the correct reaction between MnO2. Maybe I'm skipping something, maybe I'm missing something. We already have gone for the answer, but let me just re-verify the reaction between MnO2 and NaCl. It gives you, in the presence of H2SO4, it gives you sodium bisulfate, MnSO4 and Cl2. So anyways, Cl2 is produced. That was correct. This is the product. So this is actually our Z, a pungent gas, chlorine. Moving to the next question from here. A compound A on reaction with potassium hydroxide produces a compound B, which is green in color. We all know about these reactions. We have already covered this part. So this A compound is your pyrolusite MnO2, which under action of KOH basic medium produces K2MnO4, which is green in color, plus H2, and there is no requirement of balancing this all, because we all know about the redox reactions. We can balance whatever the reaction we want, so don't panic, simply do. Then once this compound is formed K2MnO4, you got to react it with the HCl. Under acidic condition, it gets converted into KMnO4, MnO2 plus water, or water, the products are formed at there. KCl. Then finally this C compound, okay, let me just give them names also, give their proper names also. This is your B, this was the A, and this is actually C, and then C also gives with C reacts back with KMnO4, reacts back with Ki, and gives back A. So it will give you MnO2 plus I2 plus KOH. This is again A. And your D is I2. No. It's a mild basic medium. So it's a mild basic medium has been given to us. So we will make it iodate. We will make it KiO3. That is what I was telling you about, that some important part is here which we need to remember. This is your D. What has been asked? A and D will be what? Tell me. A is MnO2 and D will be KiO3. B is the perfect answer. These are some set of reactions. Yeah, thank you, Prodos JEE 2025. B is the perfect answer. So there is no such question which we cannot do if we are absolutely clear on what we are studying, how we are studying, and we are making a proper short note about all the reactions which we are writing. I have already told you there is no requirement of rote learning all of that equations or the reactions which we showed about KMnO4 or K2Cr2O7. Why is it so? Because they are mostly redox reactions and we know how to balance redox reactions. So we can balance whatever the reaction is there. We must know one thing, that what reactant is going to what product. This is what we need to know, then we can balance it. Now let us come to the another question. Question says that assuming a complete ionization, same number of moles of which of the following compound will require the least amount of acidified KMnO4 for the complete reaction. So guys, how does this reaction go on? Let me just give you this idea that KMnO4, okay, you can do whatever the method you want to do. I would go for gram equivalence method. So gram equivalent of KMnO4 must be equals to gram equivalent of whatever the reactant is there. Reactant, this let it be a reactant, another reactant, this one be the another reactant. So it is asking me the same number of moles, which of them will be having least amount of acidified, this will be needed by least amount. So I think this is equals to number of N factor multiplied by number of moles of reactant. Let us say this is a constant, then this should be the least. Let's say N factor is least for which of the following compound, which of these compound. This is iron in positive 2 oxidation state and sulfur is in positive 4 oxidation state. So if you oxidize them using that oxidizing agent, it will be oxidized to Fe3 plus, or sulfur will goes to SO4 2 minus. So now this is positive 3 and this is positive 6. So the N factor is actually, for this compound, the N factor will be 2 to 1, it is 1 plus 2 plus 2, 3. Try finding out the same for this N factor, because I know this under oxidation it will go to Fe3 plus CO2. This is positive 4, this is positive 3, and this is positive 2, and this is positive 3. So again, N factor will come up as 3. I guess the correct answer should be, so whoever is having the maximum, the least number of things, D should be the correct answer, I guess, because in this case only this will oxidize to Fe3 plus only. This will be oxidized to Fe3 plus only. There is no need to oxidize any other thing, because sulfur is already in positive 6, iron is in positive 3. This is only goes there. So this N factor for FeSO4 comes up as only 1. If 1 is the N factor, it will require the least number of moles. The correct answer should be D. Yes, it is. Sorry. Another question. KMnO4 reacts with oxalic acid in this reaction. A 20 ml of 0.1 molar KMnO4 is equivalent to what? For these reactions, always apply the law of equivalence, that gram equivalent of KMnO4 must be equals to the gram equivalent of whatever the reagent we are using for H2C2O4. So you guys must know what reaction would it occur from here, what reactions will go on, what reactants we are using, what products will we make. Then you will be getting a sufficient idea about the question. Let us take this thing as what we reaction carrying out into acidic medium. So number of moles are very well known to us, 20 ml into 0.1 molar into N factor. So this is your, actually we can call it like milligram equivalent, okay, milligram equivalent of potassium permanganate KMnO4, and this must be equals to what? This must be equals to what? Out of these things. So H2C2O4 will definitely be converting into CO2, so its N factor will be n factor will be just 2. So now you apply this equation and try to find out if it is possible. And this n factor will be, in acidic condition, it will be 5. So ultimately, let me just find out the number of milligram equivalent for KMnO4. For KMnO4, the milligram equivalent will be how many? For KMnO4, how many milligram equivalent can you see? 20 into 5 is 100, 110 milligram equivalent. 10 milligram equivalent. Now you have to check it out which one of them is having 10 milligram equivalent. Which one of them will be having 10 milligram equivalent? Here we have 50 into 0.5 into 2. Basically, it is giving you 5 gram equivalent. Incorrect. Then it has 20 into 20 into 0.1 into 2, 4 gram equivalent. No, incorrect. 20 into 0.5 into 2. So 2 gram equivalent, I guess. I guess it is also incorrect. 20 gram equivalent. This is correct. 10 gram equivalent, 10 milligram equivalent actually. All of them are milli only. D is the correct answer, I guess. That was all simple calculations that was needed. It wasn't a very tough question, by the way. Was not a tough question at all. Anybody could have solved this question. What it required was the proper concentration upon what we have given, how to use it, and the calculations. My calculations are far good. That's why I'm pretty much able to solve such question. This is highly easy question to all of us. Which of the following can decolorize? This is positive 7 oxidation state and it works as an oxidizing agent. Oxidizing agent can oxidize to anyone which is present in the lower oxidation state. This is positive 4, this is positive 5, this is positive 4, and this is positive 6. The only compound which is in lower oxidation state is SO2 that can undergo oxidation. So A will be the correct answer. See how easy these questions are. Next is XO2 is fused with alkali. I think we have done this reaction many times. Manganese is the correct answer. This is talking about pyrolusite MnO2, which in the presence of fused with oxygen and air produces K2MnO4, which is green in color. Sorry. This is the reaction K24 plus only water. Okay. Balancing you can do it by your own, because we all know redox reactions and their balancings. So M1 is the correct answer. Rest all the questions you should do by your own, guys. Let us take all these questions as homework and download these notes from our Telegram channel. The link is given in the description. All of these questions will be done from your end. Now I'll come to the another important compound called as potassium dichromate. The another important compound is potassium dichromate, K2Cr2O7, orange colored compound. How is it prepared? A similar kind of reaction will occur where we are reacting chromite ore. Chromite is iron and chromium ore. FeCr2O4 is called as chromite ore. Fusion of chromite ore with sodium or potassium carbonate. Sodium or potassium carbonate in free access of air produces chromate ion. So iron chromate when reacted with sodium carbonate in presence of oxygen produces sodium chromate, Na2Cr O4. We call this compound as sodium chromate. This was earlier FeCr2O4 or chromite ion along with iron oxide and CO2. The solution is filtered and acidified with H2SO4 to give a solution from which orange sodium dichromate ion Na2Cr2O7 can be crystallized. So this reaction is happening here. Let me just remove this green color. It is unnecessarily spoiling the reaction given. The reaction is this one. Sodium chromate, which we earlier formed Na2Cr4, is now allowed to basically actually both of them are having the same oxidation state, as I can see. Positive 6 and that too also has positive 6. So basically it is doing this reaction. It's a reversible reaction. In basic material it's come back to sodium chromate, and its acidic condition it goes to sodium dichromate. So Na2Cr2O7 is more soluble than K2Cr2O7. That is why K2Cr2O7 is prepared by treating the solution with sodium chromate and KCl. Then this double displacement reaction occurs. You are getting potassium dichromate. The orange crystals of potassium dichromate are crystallized out. So this reaction is very similar, as I told you. The reaction is very similar as in yellow colored chromate ion, Na2Cr4 we earlier were using. It can be converted into dichromate ion under basic conditions. This can be converted under basic condition. Not under basic condition, yeah. Give me a second, guys. It's stuck somewhere here. Yes, so where were we? Yeah, so dichromate ion and chromate ion are very much interconvertible to each other depending only upon the pH or the nature of medium. In acidic condition, chromate ion gets converted to dichromate, and in basic condition dichromate gets converted back into chromate ion. That's how they are interconvertible. So I would rather simply go to the properties of this compound, potassium dichromate. We'll come to its chemical properties also, or we'll finish it anyhow, and then we'll come to the F block element. We'll reach out to their further properties, and then we'll finish up the entire session. Properties: sodium dichromate, Na2Cr2O7 and K2Cr2O7, these both are oxidizing agent. They all are having their chromium in positive 6 oxidation, the highest oxidation state possible for chromium. So this can only undergo reduction That's a good oxidizing agent. Na2Cr2O7 is extensively used as an oxidizing agent in organic chemistry. As I told you, one of the example, alcohols are converted into carbonyl compounds using this process. K2Cr2O7 is also used as primary standard in volumetric analysis. Primary standard. What is the meaning of primary standard? As titrant we use it, titrant. A solution in redox, actually in redox titrations we use K2Cr2O7 as a primary standard, because this is something whose concentration can be known, and you already know the N factor. Using that equation of gram equivalent of 1 equals to gram equals to 2, you can find out the unknown parameter of the unknown quantity. That's why we use it as a titrant. In acidic conditions, K2Cr2O7 gets converted into Cr3+, goes for reduction, and it only works as an oxidizing agent in acidic condition. So you don't need to be worried about just like we used to do in potassium permanganate, because in permanganate the oxidation as an oxidizing agent, potassium permanganate could have been used into any kind of medium. It could be acidic medium, it could be basic medium, it could be neutral medium as well. Here there is no as such medium, only acidic medium is allowed, and that is why this is very much pretty much able to convert it back into Cr3+ and oxidizing whatever the substances it has been reacted with. So take these examples. For an example, I- is converted to I2, H2S with -2 oxidation state will be converted to the sulfur 0 oxidation state, Sn2+ goes to 4+, 4+2 goes to 3+. These were some set of chemical reaction that we remember. Only remember what is going to what. No need to remember about complete balanced chemical equation. We know the balancing, we can do balancing by our own. What are the uses? Potassium dichromate is a very important chemical compound in leather industries as well as in the oxidation of the many azo compound. So it is also used in chromyl chloride test. I guess it's very important, guys. It's very important. Let me write the test. This is your chromyl chloride test. What is this test all about? So we have one salt of chloride, could be NaCl, KCl, whatever it is, which then is reacted with potassium dichromate in 3 part. 3 is not required, which we can balance by our own, and then once it is added with H2SO4, warm gently, produces deep red colored vapors of CrO2Cl2, which is called as chromyl chloride. These so formed red color vapor confirm the test of Cl- ion, and once it is passed through NaOH, these CrO2Cl2 gets back converted. This CrO2Cl2 gets back converted into CrO4 2-, which is dichromate and Cl-. So again, it's a reversible reaction. So this confirms the test of yellow color solution is observed, which confirms the presence of Cl- ion. It's a confirmatory test is used in the analytical chemistry of finding out the Cl- ion. So confirmatory test of chloride ion you will come to understand while we'll be dealing in the analytical chemistry or practical inorganic chemistry, where you will find that Cl- ion will be confirmed by using this chromyl chloride test. Now let us solve some questions related to it, and then we'll come to F block elements, the last and final part of this chapter, the remaining one part of this. The fusion of chromite ore with sodium potassium carbonate in free access produces, yes, it produces a chromate ion. Chromate ion is produced, which in acidic conditions leads to the formation of dichromate ion. Which of the following statement is false? Na2Cl2 is less soluble than this. Wrong, it is more soluble. That is why we have to convert it into K2Cl2O7. It is used in volumetry. No. Tetrahedral in shape, yes. Okay, it is, which is false. I think A is correct. Man, statement is false and it is used in it. This is also incorrect. This is also incorrect. I remember where we were studying this part, that Na2Cl2O7 is more soluble. See? Anyways, we'll have to check it. You can check the solubility data, don't worry everyone. I will check the solubility data here. Actually, that was incorrectly written, and that is what I'm thinking, because Fazan rule also explains the same part. How come potassium will be more soluble, guys? This is true, actually. This is true. This is true. And I guess that was incorrectly written there in the notes. That was incorrectly written. Let me just correct this part. My bad. Pardon, please. This part is incorrect. And this is more, instead, this is less soluble. Right? Let me just explain this part also. Not a problem at all. Let me just explain. So what happens, everyone? We all know that coming to K2Cr2O7 versus Na2Cr2O7. Rest everything is same, only the difference is of K positive and Na positive. It is smaller in size, and Na plus has higher what? Charge density, and this was the order of size. So this one has charge density, it does more polarization or polarizing power. It has more polarizing power, thus imparts more covalent character. And solubility we are talking about the solubility in water. So which one of them will be having higher solubility? None other than K2Cr2O7, more soluble. This is how we can explain it. Now you people try solving this question. I'll be back quickly, getting some water actually for me. Now allow me just 5 minutes. I'll be back very quickly. Please try solving this question. This is not good. Yes. So where were we, everyone? Now come over here and let's check this question. So I asked you people to solve this question by your own. Hopefully you have solved it. Potassium dichromate when heated in the concentrated sulfuric acid and soluble chloride brown red get, I think, CrO to Cl2 chromyl chloride test. We all remember this test, I guess. What was that test? Let me just remind you. K2Cr2O7, and when it is reacted with NaCl in concentrated H2SO4 solution, then it gives you chromyl chloride CrO2 Cl2. This is the reaction. Anyways, what will be the byproduct? I'll give you. The byproduct will be highly based upon sulfates only, maybe like K2SO4 or like that. Which of the following is not formed when H2S reacts with H2Cr2O7? So H2S will be oxidized using K2Cr2O7, and the reaction is happening in acidic medium, only happens in acidic medium only. So this will produce, the H2S will be converted into sulfur, or K2Cr2O7 will be converted into Cr3 plus. So Cr3 plus is, this is your Cr3 plus, this is correct, this is also correct. K2 over this is incorrect. This is Cr2 plus which is not formed. A is the correct answer here. Now I'll move forward to another question, and you people try solving some questions by your own. This is something you can solve it by your own. K2Cr2O7 on heating with NaOH gives you what? Dichromate in presence of basic medium will give you chromate ion. So it will give you CrO4 2 minus. And acidified K2Cr2O7 solution turns green when added to this because of the formation of chromate. Okay, sodium sulfite. Okay, I thought it is talking about the sodium carbonate. Anyways, this is in positive 4 oxidation state. It will be converted into positive 6. And itself, it will go for positive 3, and sulfur will go to plus 3. It is correct. Now, what is the uses of D block element that we do? How do we use the D block elements, everyone? So coinage metals are used to form the coins, such as copper, silver, gold and all. Iron and steel are mostly important used in construction material. Titanium oxide is used in the pigment industries. Do remember this point. These points are highly enough as I use, and you can use them whenever any question such comes. We haven't seen such questions till now as such. MnO2 is used in dry. This kind of question have appeared, I remember so. Like nickel battery, some of the metals can used in battery preparation kind of thing question was there. Battery industries, we use zinc and nickel, nicad batteries, and this is your none other than Daniel cell. Group 11 coinage metal are used for the making some alloys and some silver alloys and all. V2O5 catalyzes in a contact process. Titanium with aluminium, this is called as Ziegler-Natta catalyst, used in the polyethylene processes. Hydroxy polyethylene of ethylene we use in the polymerization processes. Ziegler-Natta catalyst, high density polythenes are formed. Another uses are iron catalysts are used in Haber process to form ammonia. Nickel catalysts are used in hydrogenation of fats. Unsaturated fats are converted into saturated oils. Waker's process is also there, where we oxidize ethine into ethanol by using palladium chloride, which is another important compound of palladium. Nickel complexes are very much useful. Nickel complexes are useful in the polymerization processes, and like this. And then photographic industries are using special light sensitive properties of silver bromide. Silver bromide is a very important compound used in the photo, and in fact the old time photographic films we used to use it. There we used to use these kind of rolls, photographic rolls. Then a question. Oxidation of SO2, contact process, V2O5, it's a directly remembering thing. You cannot do anything else apart from directly rote learning this part. Then another question, V2O5 contact process. This is your titanium chloride, Ziegler-Natta, used in polymerization. Waker's process. Okay. Oxidation of ethine into ethanol. Oxidation of ethine into ethanol, that is used in PDCl2 is used Waker's process. Now nickel complexes, actually there was a use I saw somewhere. See, nickel catalysts are enabled to hydrogenation of fat. Nickel complexes are useful in polymerization of alkynes. Okay, such as benzene. Okay. So alkyne can be converted into benzene. So alkyne, where is written alkyne ethine to ethanol is fine. Polymerization of alkynes, nickel complexes, and then this will come, which is there. Ziegler-Natta will come to ethylene. Next, photographic thing, whenever you have to use the photographic film, silver bromide is used there. Waker process, PDCl2, very factual question. And finally, now we have come to F block elements, and we'll finish all F block elements very soon. Yes, so guys, lanthanides, there are total 28 elements starting from lanthanum to lutetium, which is 58. Sorry, not lanthanum, right after lanthanum, 57 is the lanthanum, 58 is actually the element which is cerium. From cerium to lutetium, that is up to 71, and then from 90, which is thorium. So from 90 to we have 103 lawrencium. These are the elements, total number of 28 elements we have, and these total 28 elements actually are regarded as the total 28 elements. These are regarded as the F block elements. F block elements are lanthanides and actinides. So the very first set that you can see is the lanthanide. These are lanthanides, and right comes after the lanthanum 57. These comes right after the actinide, actinium, that is why we call them actinides. Their lanthanides resemble to one another because they have only one stable oxidation state, that is Ln plus 3 oxidation state. You all remember that time I told you about the lanthanide contraction, and there I was teaching about Ln 3 plus I was taking. Every single was taken in the 3 plus oxidation state. So there are small changes in size and nuclear charge along the series of the otherwise similar elements. Chemistry of the actinides are much more complicated. They have variable oxidation state and they are radioactive in nature, and that is why they create problem in their study. And that is why only some questions have been asked previously in the examinations about actinides. Actinides not have been asked too much. The chemistry of actinide is difficult. Why? Because they show a wide range of oxidation state. Lanthanides are what? Lanthanides are 14 elements in the 6th period or in 7th. 6th is the lanthanide, 7th is the actinide, and 6th period, 6 from 58 to 71. Which element is not considered as lanthanide? Lanthanide, which is not the lanthanide. Okay, say par and pum some. Okay, uranium. Uranium is then lanthanide. Lanthanide, their electronic configuration we have lanthanum, cerium, then we have praseodymium, neodymium, promethium, samarium, europium, gadolinium. So why is gadolinium is so dark there, bold in the text? Because it has some exceptional configuration. Its configuration is 6s2 5d1 and 4f7. Rest other have 4f1 d1 s2, and then f3. So I guess there is no requirement of rote learning these all, and these are not even that easy to remember. And you can check it out, guys. Like you can make it by your own if you know the general electronic configuration of them. So let me write their general electronic configuration. This is NS2 N minus 2F 1 to 14, and then N minus 1 D. D could be somewhere 0 also, 0 to 1 somewhere, it is like that. Then we have lanthanide, their atomic and ionic sizes, which decrease strictly. We already have heard about it. We call this thing as lanthanide contraction. No need to repeat everything. Number of F block electron present in cerium 3 will be how many? Now this is what we can predict by our own. I'll help you to do it. So first of all, let us consider cerium, and cerium with a 3 positive charge. So SEPAR and PUMSUM. Right after lanthanide comes, its atomic number of 58. The electronic configuration generally is argon, not argon, yeah, not everywhere argon. 6th period it comes, no? Krypton, 5s 0, most outer bossel bit, 5s 0, 2 electrons are lost. Then it is sorry, this is 6s 0 and 4f and then 5d. So how many electrons were there actually? Cerium, D1 was there, 6s2 3d1. This is 1, this is 5d also will become 0. Okay, so take this example everyone. I'm just giving you, explaining you like how do I proceed with these question. Like you can do it by your own also. This is not too tough to solve it by your own. How can we do this? Take this example. So this is like for cerium it will become 6s2 and 5f1 and 3d1 5d1. So if you go for cerium 3 positive, you need to remove the electrons from 6s0 because outermost will be removed very first, and then then it will become 4f1 and 5d0. Now how many electrons can you see in f subshell? 1. So correct answer will be 1. That is how I do. That's how I solve these questions. Oxidation state, the very common oxidation state is most common oxidation state is +3, but it also shows +2 and +4, and especially it has been shown by those elements which after showing +2 or +4, either they undergo half shell or completely full shell or completely nil shell. Under these conditions it can be used to find these oxidation state +2 and +4. So mostly it gives you +3, and +2 and +4 are only found in the case where we can have this set of number. Then C and Tb exist +4 in oxidation state. Why? Because cerium can have 0. After showing +4 oxidation state, it has 0 electrons in F subshell, so it is a stable configuration nearest to the noble gas configuration it will have, and and then +4 oxidation states, but only in oxides they show PRO, NDO, TBO, DYO. Then we have oxidation states of europium and then YB exhibit +2 oxidation state. Allow me a sec. Sorry. Yeah guys, so actually the oxides, what we were discussing that most commonly they show +3, but they also show +2 and +4. But +2 and +4 shown only in these conditions, okay, not any other condition. So what we are figuring out over here, that C and TB show their +4 oxidation state, because in this state, like C in +4 oxidation state has a completely nil orbitals, and that makes it exactly equal to the nearest noble gas. And if we talk about PR, ND, TB and DY, they also show +4 oxidation in their oxides. So maybe this oxide may form the PRO2 like that, because why, how would they show +2? So they may show their oxidation state in positive, like DYO2, TBO2, NDO2, PRO2. Now so they show only +2 oxidation state. Then EU2 positive shows +2 oxidation state in half filled shell, and YB2 positive shows in the positive full filled shell. So remember this part, guys. This is a highly important part. Remember this part, that europium and YB2 positive, they also show. It's a completely theoretical part. I must suggest you that you must read it out by your own only. In the notes, you will get it. You can get it by our Telegram channel mentioned in the comment section. Then we have oxidation state we are talking about. TB for +4 oxidation state is considered to be the TB4 plus in its oxidation state is being considered as a strong oxidizing agent, because it is in +4 oxidation state going to +3. Why is it going to +3? I told you the most stable oxidation state for all the lanthanide. So they usually love to have +3 oxidation state. They relatively feel more stable. With increase in the F subshells, they also become more stable. Why? Because with the F subshell, their Z effective increases, extra electron also comes up with high Z effective. They are more stable in that particular state. SM2, if we talk about the SM62, SM in +2 oxidation state, it behaves like a reducing agent, because it also wants to go to +3, which is also the most stable oxidation state. Something which is already undergoing oxidation will act as a reducing agent. Something which already undergoing reduction will act as a oxidizing agent. That's how we define them. General characteristics of lanthanide, they all are, lanthanides are silvery white soft solid. They tarnish rapidly in the air. They get oxidized easily. Their hardness increases with increasing atomic number, and most hard is samarium, which is SM, which is exactly steel hard. And their melting points range from the 1000 Kelvin to 1200 Kelvin, and samarium melts at 1623, which is the hardest substances among all. Then they have typical metallic structure. They are good conductors of heat and electricity. Density and other properties change smoothly except europium and YB, and occasionally for SM and TM also. Then many of the trivalent lanthanides are colored with both in solid state as well as in aqueous solution due to the presence of F electron. They undergo FF transition, as I told you. Neither of the La3 plus or La2 position show any kind of color, and rest also do so. Because La3 plus and Lu2 plus have no unpaired electron, that is why it has been shown like this, no unpaired electrons. Then absorption band are narrow because of excitation of F level, and lanthanide ions F0 type, these, and F14 type, these all are paramagnetic. Rest others are paramagnetic because of the presence of F subshell. And you can fill the electronic configuration by your own. You can check it out by your own, because we all know the 3 electrons that will be removed from their Ln3 positive state is ns2 electron and then n-1 d electron. Nf electrons will be there remaining as a unpaired electron. So wherever it is n14, whenever it is like 14 electrons are there in F subshell, or if there are like 0 electron in F subshell, then only under these conditions and under these conditions they only act as a diamagnetic. Rest all other are paramagnetic. Then ionization enthalpy, first is around 600, second is around 1200, comparing to that of calcium. Lanthanum, gadolinium, lutetium, they have abnormally low ionization enthalpy due to their stable +3 configuration. Okay, because they acquire +3 oxidation state, and that's why their ionization enthalpies are low. They remove their electron and they become stable in their +3 oxidation state. Then in the, okay, where you get it, by the way, it actually, let me tell you, lanthanum has this will have configuration F0 and F7, and this will have F14. These configurations they acquire, and that is why they have been they've been found stable in their +3 oxidation state. Their chemical behavior in general, the the earlier members of the series are quite reactive. In their chemical behavior, generally, the earlier members series are quite reactive, similar to calcium, but with increase in the atomic number, they behave more like aluminium. Okay, like +3 oxidation state they show. Chemical properties, since we all know they show general characteristic, general oxidation state of +3. So now using that +3 oxidation state, what you can do is apply all of these reactions. Lanthanides on reaction with carbon form carbides of many oxidation state, Ln3C, Lnc2, Ln2C3. Oxygen, they form +3 oxidation state of lanthanum oxide. You must find that oxidation states are very common: +3, +3, +3, +3, +3, +3 and +3. Now it has become very easy to find the compound. Whatever the compound you want to make, you may make. Now is the time for actinide, the final topic of the day with actinide. So actinium, thorium. Actinium is not, this is a D block element only, but rest other right after it, all 14 elements from thorium to lawrencium, they all come under the category of actinide. We don't need remembering all the electron configuration. It's too tough to remember. We can just apply the common sense, just like I used to do, and similar kind of configuration will be there. They also have +3 oxidation state as the most common oxidation state, but right after that they also show variable oxidation states, and that is what makes their study very difficult. Their atomic sizes we talk about, they continuously keep on decreasing. That is called as actinide contraction. Just like lanthanide contraction, they have actinide contraction. Then talking of their physical state, they usually are solids in nature, and their structure variability is obtained due to the irregularities in their metallic radii, which are far greater than in lanthanide. So basically, lanthanides have usually similar kind of structure, but they do not possess, they possess multiple type of structures. Next we have Coming to the oxidation state, you can find the varieties of oxidation state, just like we saw in 3D series. Manganese used to have so many oxidation state like that. So Pu, plutonium, have various oxidation state 3, 4, 5, 6, 7 also. The actinides have more compounds in positive 3 oxidation state. As I told you, positive 3 is always the most stable state for both actinides and lanthanides. And then we have however, positive 3 and positive 4 oxidations tend to hydrolyze, and due to uneven distribution of oxidation state, this is unsatisfactory to review their chemistry in the terms of oxidation state, and that is what it makes their study difficult to study. It makes their study very difficult, and that's why not too much questions come out of this particular segment of actinide. But yeah, for lanthanide it's fine to have some similar kind of or some common type of questions, either based upon their chemical properties or their positive 3 oxidation state, or related to somewhere where we found the number of electrons found in apse of shell, diamagnetic, paramagnetic kind of. This kind of questions sometimes appear. There is a greater range of oxidation state, which is due to the fact that 5D and these levels are of comparable energies. Then we have general characteristic. Actinides are highly reactive metals, especially when they are finely divided in their powdered form. The action of boiling water gives a mixture of oxides and hydroxides. That is what I told you. It has been written there that where it was somewhere we read about it, that they undergoes hydrolysis in their positive 4 form. They undergo hydrolysis with the availability of F subshells. Water can attack easily on them and can form the hydroxides and oxides. Combination with most non-metal takes place at high or moderate temperature. Hydrochloric acid also attacks on all the metal, but most slightly affected by the nitric acid, owing the formation of protective layer of oxides. And alkalis have no action on these metal. Ionization enthalpy of actinides not accurately known, but lower than that for lanthanide. Okay. Because 4F is like 4F is more closer to nucleus than the 5F. 5F is farther, and that's why its ionization enthalpy will be lesser. The energy required to remove the electron from 5s subshell will be slightly lesser, and these are more effectively shielded from the nuclear charge than 5F. Okay. Then the uses, if we talk about their uses, then check it out everyone. The best single use of the lanthanide is the production of alloy steel, plates and pipes. And a very well known alloy is mish metal, which consists of lanthanide metal by 95% and iron 5%. And this is, okay, remember this part, it's an important part. So good deal of mish metal is magnesium based alloy to produce the bullet shell, and this mixture of mixed oxides of lanthanide are employed as catalysts in petroleum cracking. Some of the individual lanthanoid oxides are used in the phosphor, television screen, and this. So this is what the uses of complete F block elements are, and just have a quick revision over there. Now we are ended up with this chapter completely. All the things have been covered in this chapter. These notes will be available only on our Telegram channel that is given in the link of description. Do follow us, subscribe us, and guys, enjoy your sessions with us freely, completely available with your Sanjay Arya sir. Complete chemistry will be covered over here. Best use of lanthanide for the production of what? I guess alloy steel. Then the correct electronic configuration, spin only magnetic moment. Okay, this question has been asked somewhere, okay, in JEE 2020. But we don't fear of anything, guys, because we remember everything. Yeah, we know everything. We know about gadolinium shows for F7. We know about what was that? Lutetium 3+ has 14 filled electron there, and lanthanum 3+ has 0 unpaired electrons, 0 electrons in F subshell, and gadolinium has F7. So this is something which is important that we must know, and I'll give you the answer. Okay, correct electronic configuration, spin only magnetic moment, gadolinium 3+. So 7.9 and 4F7, I guess correct answer. Woo, boom. That's how I do, and that is what I want you people to be very comfortable about. Say one more question came in 2020. Electronic configuration of bivalent europium and trivalent cerium are. Cerium 3 plus has 1 electron in it, so this will become F1. Only question, this could be correct answer, I guess. And after gadolinium, God, whatever I do, it always become correct, and this kind of comfort zone I want you people to have. Which is not the correct statement? La3 plus is diamagnetic. Is it? Yes, true. Cerium plus true. Lu has 14, true. 3 plus is pink. Let me check. I think YB 3 plus is fully filled. Correct. This is fully filled. No color. Next question. Arrange these in increasing order of their ionic radii. What do you think? They continuously decrease, no? We know. C. Lanthanum 3 plus comes, then so how do we remember this thing? Well, we going left to the right. What happens? Size continuously decreases. Now you check it out. So La3 plus will be the largest, followed by C3 plus, followed by PM, and then YB. I think A is correct. A is fine. See. So guys, these are some set of homework that you to do by your own, and I think I have completed everything by my end. Now it is your time that you should solve this much number of questions I have provided you. So many questions are there. I think these are very enough for you for your preparation. I will come up with another important session in my upcoming class. Take care until then, and love you all. We'll see ya soon. Bye bye guys. Take care and good night.